Okay. All right. Welcome back. Can you guys at the back hear me? Is it working? Okay, thank you. All right, today is going to be Formal Developments Day. I'm going to talk today about some aspects, not the full thing, some aspects of the renormalization and the renormalization group. And later on, I will talk about a further refinement of the classification of leading and subleading operators that we've been talking about. So without further ado, let me start with renormalization. The first thing I want to cover is the fact that the theory that I've been telling you, that the theory is renormalizable. The operators that I'm going to look at, again, have this general form. I changed a little bit the notation. You should get used to it. I will not apologize. Sometimes notation change, the meaning doesn't. I used to call the boson fields phi and the fermion fields psi. Here it's called BNF, or bosons and fermions. And D is a covariant derivative. Has a coefficient that has a number times a appropriate dimensional coefficient to ensure that the whole the product of C times O has dimensions 4. And in order to do that, then this delta has to have the dimension of the operator minus 4, which is specifically listed here. Okay. Okay. The statement that the effective Lagrangian is renormalizable. How do we go around proving it? You can consider any effect. You can regularize the theory by any means that you find convenient, like dimensional regularization. Okay. And so when you do any graph, dimensional regularization is not confined to theories that have vertices of dimensions 4 or less. It can be used for any theory. So you can imagine doing a calculation with any term involving any number of terms, either in the light theory or in the effective operators. Those are, because the effective operators are local, the vertices are the usual Feynman type vertices, except they may have many legs, and they might have many powers of momentum inside. But in principle, you can do exactly the same calculations that you do in regular renormalization studies of renormalizable theories. Once you do that, you do a calculation, you find that the graphs that you evaluate when dimensionally regularized appear with poles of 1 over dimension minus 4. Could be to one loop, you will have, and I'm going to call that quantity dimension minus 4 epsilon. So you have poles in epsilon, have factors of 1 over epsilon. In one loop, you get 1 over epsilon. In higher loops, you get higher powers. But the point that I want to make is that the coefficient of this 1 over epsilon or 1 over epsilon squared of all the poles are always polynomials in the external momentum. There's never a logarithm multiplying a 1 over epsilon. There is never some rational function of the momentum. It's always a it's always a polynomial of the external momentum. And so the divergences are associated with this thing. And second, the theory, the full theory, and I've been insisting on this, satisfies all the local symmetries of the light theory. And so you have, and this is respected by dimensional regularization. That's its virtue, that it respects the local symmetries. And so you have a theory where the divergences are, as in the one examples that you've been looking at in your career, they're polynomial in the external momenta. The divergences obey the symmetries. And what I mean here is that the divergent terms, regularized, obey the symmetries. So you have an expression that has a 1 over epsilon or whatever, 1 over epsilon squared or whatever, multiplied by a power of momentum corresponding to a graph. And this exact vertex, power of momentum thing, corresponds to an operator. Yes?
These operators can be higher dimensional?
Can be a higher dimensional operator.
And redundant operator?
And can be a redundant operator, absolutely. Actually, if you actually work it out, the redundant operators really take care of themselves, but I will not go into that. It's a detail. But it absolutely could be a redundant operator. It just shows up as an okay, and therefore, because the divergence satisfies the symmetries and corresponds to an operator, divergence can be absorbed in one of the infinite number of coefficients that I have. Because I've listed them all, I have a divergence that corresponds to an operator that satisfies the symmetries, and therefore it must be in my list of operators. It must correspond to one of the COs, and therefore the divergence can be absorbed in redefining that particular CO. And that, since I haven't specified what kind of graph, will occur to every graph that has a divergence. And this simple argument shows that the theory is renormalizable. All the divergences correspond to a local operator that satisfies the symmetries, and therefore it's in the list. So, as I mentioned earlier, much earlier, then the issue is not renormalizability. The theory is renormalizable. The problem is that we have very many coefficients, and so one needs to be able to do that, to deal with that, if the theory has any predictability at all. Renormalizability is not an issue. You don't have to use dimensional regularization if you don't like, but what is really, really, really useful is to ensure that the regulator, whatever it is, respects the local symmetries. If your regularization breaks the local symmetries, and doing renormalization that way is awful. It's really awful. It's difficult. There are books that do that. There's early books by Bogolyubov and Shurkov. It's a very old book, like 1960s book. They do that. They renormalize QED, in fact, with I think it was a cutoff, which doesn't respect the local symmetries. And the results are very complicated, unnecessarily so. But there is still a renormalization question. And this is the following question. Could it be that operators high in the hierarchy renormalize those lower in the hierarchy? You might say, well, it doesn't matter. It's still a renormalization effect. But it matters if, for some reason, you are interested in calculating the renormalization group running of the coefficients. Because if you do that, if this does happen, and you want to calculate how a low-dimensional operator coefficient runs, you will find that because of this feed down from higher dimensional operators, for example, in the weakly coupled case, to lower dimensional operators, that the running of the low dimensional coefficients depends on the high dimensional coefficients. And in principle will depend with a high dimension of any dimension. So this thing would imply the running equation cannot be calculated, cannot be measured in a way, because the precision to which you can measure coefficients ends at sufficiently high level, and so these guys will eventually become unavailable to you. You cannot measure them, not because the coefficients themselves are small, but because lambda is large. Lambda, capital lambda. The scale is very large. So the effects of these guys, the high dimension, is unobservable because of limited experimental precision and because the capital lambda, the scale of new physics, is very large. But these coefficients can all be of order 1. And so if you do that, then the right-hand side of the RG equation cannot be determined, and the running itself is unavailable to you. That would be very unhappy situation. Really lack of predictability, because then the way the coefficients behave depends on quantities that are not acceptable for you to measure. So if we're going to have a hierarchy, this better not happen. And let's see if that's true or not. In fact, you might expect it will be true. I mean, it doesn't happen. This really doesn't happen. So let me go back to a type of graphs that has a bunch of loops. Each of the 5 vertices here is produced by one operator, O sub v, where little v is 1, 2, 3, 4, 5. And from this, you can calculate its naive degree of divergence. This is a straightforward calculation. And you get expression here, which can be expressed in terms of the dimensionality of the vertices, of the operators generating the vertices, and the dimensionality of the operator. These guys renormalize. And if you're wondering about these little slashes here, what I mean by this is that these external lines have been amputated. So there's no propagators here, just so this vertex 4 has 1, 2, 3, 4, 5 legs. 3 of those are internal, 2 are external, but they don't have propagators attached to them. I can rewrite the degree of divergence in terms of my indices. Now, of course, n divergence doesn't depend on any parameter. Well, on this arbitrary parameter u I introduced before in this thing. But if you actually write this out, you find that the u dependence cancels out. All right. So each OV has it gives, in a sense, a factor delta OV, and you have this relationship again. Okay. Now, the naive degree of divergence is associated with the leading divergence in a graph. So typically, you get a factor of a cutoff to the power n divergence. That's what you do when you do this. In dimensional regularization, you don't get. I know you don't get you don't get cutoffs, but you can make a correspondence between the powers of 1 over epsilon and powers or logarithmic dependence on the cutoff in a standard way. That's a standard renormalization parallel that one can derive. If I want to obtain the group, I need to find out more details about the divergences. So I'm going to be talking for the next few minutes about infinities. Now, if we go and look at this expression here, if u is less than 4 or equal, less or equal than 4, as I will assume, and all these guys are positive, all these indices are positive, this quantity here is positive. And so if you have a, So you have a divergent graph. This object is greater or equal than 0. I'm going to write on the board like that quickly here. And div equal to 4 minus u. L, I forgot to say, I'm sorry, is the number of loops plus the sum of S O sub v minus S O. And for a divergent graph, this is greater or equal than 0. I've assumed this is positive. This is positive. So when 4 is greater than u, and if SOV is positive, then you have that this guy four minus UL plus the sum SOV is greater equal than SO. The index of, so these are the vertices, and this is the operator being renormalized. Okay? So we have those relations. Very simple. So, if this is true, then each of these guys will be greater than this guy. I'm sorry. If for divergent graphs you have this, then operators that can renormalize with lower, that can renormalize O, these guys renormalize O only if they have lower indices. Indices are positive. So if this is positive, then I cannot have any of these guys be larger than this because this inequality would be violated. You know, I cannot have this. And so the OA renormalize operators with lower or equal index. So these guys are each, I'm being confusing. Sorry. So let me just go by this carefully. So if the indices are positive and 4 minus u is positive, then this equation holds. SA is greater than SO. That's it follows from the previous expressions, from this. And so operators, the OA, renormalize operators with lower or equal index. That's what it means, provided this is true. And so in that case, the U is consistent. And so the question reduces to, that is, you will never get this. This just doesn't happen, provided the index is positive in this region. 4 greater than, 4 greater or equal than u. So it reduces to saying whether my index is positive or not. And it turns out, from the previous expressions, very straightforward, that this is true. That the index is positive, provided this is positive. And this is true, provided the dimension of the operator is at least 4. So everything holds out nicely, provided I don't have dimension 3 vertices in my theory. These are super renormalizable operators. And the reason they are problematic is that in the spirit of effective theories, all coefficients, all dimensional coefficients in the effective theory, well, they're associated with the scale lambda. And so you might think that these operators that have dimension 3 will have a factor of lambda, not the power of 1 over lambda, but a factor of lambda in front. And so every time you insert or you have one of these guys appearing in a graph, it gives you a positive power of lambda and therefore screws up the counting in the sense that lower dimensional operators contribute in the wrong direction for finding in generating the renormalization group running. So these guys require extra care that I will go to in a minute. So if you have 0 naive degree of divergence, that means the divergence is logarithmic, and the renormalization group running is generated by it and has this typical form. This is from the estimates that I've been doing earlier, like the one I did yesterday, and this is just dimensional analysis that one gets. However, if the naive degree of divergence is positive, then the renormalization group running is not generated by the leading divergence in the graph, but in fact by a logarithmic subdivergence in the graph. And because it's a subdivergence, it appears with a factor of this sort. So you get this guy, and then you get a suppression factor of a light mass over lambda times n divergence times the power of lambda. This type of effects I will call subleading because they are suppressed by a small scale over the large scale of new physics. So we were interested really in graphs that have naive degree of divergence equal to 0. The other ones provide subleading effects. So this is what this says. When this occurs, this is true. This is basically this is dimension of OV minus 4, and this is the dimension of O. Okay. And so the issue in this language of the deltas with super renormalizable vertices is that this delta, which is dimension of the operator minus 4, is positive except for this super renormalizable vertices of dimension 3 for which the delta is equal to minus 1. However, if you have a super renormalizable vertex which has a factor of lambda in front, not any other scale, but lambda in front, then you have a problem. Let me illustrate that with a simple model, with a scalar model. So suppose you have a scalar model with a quartic potential and you also have a super renormalizable vertex of order with scale of order capital lambda. Let me put a minus sign here. It doesn't matter. So how does the potential look? This is the potential. Well, minus the potential. If you have no lambda, no capital lambda, no super renormalizable vertex, the potential is nicely of a nice parabolic shape. Like that. So this is the case of lambda equal to 0. And here, the potential is approximately 1/2 m phi squared. This is a function of phi. This is v. No problems. If you have a potential term that goes like phi cubed, things change because, or necessarily change, because lambda is very large compared to m. So in that case, the phi cubed term is positive. I'm going to kind of make a dot line here, and negative for negative phis. And this drop is steep because lambda is very large. So what you get is a rather steeper behavior on this side. But here, you get a dip. Produced by the cubic term. Eventually, the quartic term wins out, and so you don't have a problem with having no vacuum. The thing really goes to infinity on both sides. But in between, you have a minimum that is not at 0, and you can calculate what the mass would be around here, around that minimum. That is the curvature of this. The curvature is of order lambda. So if you have a large cubic term, two things happen. You get automatic spontaneous symmetry breaking. The vacuum is not here, as it used to be here, but it's here, because this is lower. That's a vacuum, at least in perturbation theory. And the modes around the vacuum are heavy. How heavy? Very heavy. In fact, I'm telling you that the modes that we don't talk about are those that have energies, masses of order lambda or higher. So once you put in this thing like this, you've automatically, even if it doesn't look like it, you've actually turned the mass of your phi field into one of order lambda, not of order m, as this seems to indicate. Even though this has higher powers and blah, blah, it doesn't matter. And so adding such a term eliminates the phi from the low energy theory. So these guys, if you have any field that has a cubic term like this, it is not in the low theory. You don't have to talk about it. Now, that doesn't mean that you cannot put any cubic terms in your theory. You can, if you should. But the scale that you put here must be much lower than lambda for consistency. So this scale, in fact, should not be lambda, should be smaller scale. When you do that, then everything works out fine. Why? Because any type of renormalization effect that includes these guys, the cubic terms, now instead of lambda has a small scale, and therefore the renormalization effects actually look like this. And therefore they are subleading because the vertex explicitly has a small scale in front of it. It follows this rule. It will be then subleading, and we're back to a situation where only operators with delta positive give you the leading running of the coefficients. And if you go back to my slides, which I hesitant to do at the moment, this corresponds to the case of only lower dimensional operators renormalizing higher dimensional ones, or lower guys in the hierarchy renormalizing ones higher up in the hierarchy, as opposed to the other way around, which would be problematic. So in all, the final result is this hierarchy using the indices that I've introduced is consistent with the loop expansion in the sense that I mentioned, that the renormalization of the operators is from leading to subleading and not the other way around. So in terms of the index SO, the guy being renormalized has an index that's larger than the ones in the graph. And so it is these guys that are leading, because they have lower index, they're leading, that renormalize guys with higher S, which are subleading. Okay? So these guys, what does not happen is that the guy with a large index, subleading, renormalizes operators with lower index, to leading order. And so when you write down the effective theory, you can classify it according to the terms that have indices that are, small, larger in groups of the same index, and it's the guys in one group with low S will renormalize with high S, but not the other way around. So LS renormalizes, the evolution of LS is generated by guys below it, but not the other way around. And so if you do standard model plus dimension 6 operators, in fact, all this thing doesn't show up because there's no cubic terms there. So standard model plus dimension 6 operators, then in a way that's a closed system. You can find the evolution, the leading evolution of the coefficients, all the coefficients, standard model and effective ones, using that closed set of operators. You don't have to worry about dimension 8 operators. Yeah? Dimension operators, the 8 operators will produce subleading corrections. That is, those suppressed by light mass over lambda to some power. Actually, in this case, 2 powers for dimension 8 operators. 1 power for dimension 7 operators. Well, actually, dimension 7 operators might occur twice. Well, it's always at least light mass over capital lambda squared or higher. And that's a very small number. Okay, so this is the thing about this renormalization thing. Now let me comment a little bit whether you actually want to do this. You actually want to go through the effort. I just argue that this doesn't show up. So you just have this type of thing. Instead of having zero dimension, have zero to some power, right? Some power of these guys up here on the right-hand side. It gives you the running of this guy. This just doesn't show up. This doesn't show up. That's what I've been arguing. But the question is whether you should actually do the calculation. And I want to argue that, in fact, you don't. I've just gone through this to show that the hierarchy imposed by the indices is consistent with the loop expansion. That was the goal. But whether you should actually calculate the running, I'm not sure that's worth the effort. Within the context I'm talking. Let me explain why. If you look at the measurements that we have done today, so far today, we are sensitive to a few one-loop effects within the standard model. We are beginning to be sensitive to a very select number of to loop effects. Renormalization group is a loop effect. Running is a loop effect. So now I'm asking you to consider, you would ask yourself to consider what are loop corrections to the effective theory. And these are effects that are not going to be probed in the near future, right? Or in fact, in the not so near future, because they're very small. They are loop effects, which is a problem to begin with, in the sense that they're small. They have an inherent suppression. And on top of that, it involves effective operators. So they have an added suppression of the inverse powers of lambda. So that is a very, very small effect that we will not be probing for a very, very long time. And so for the moment, I don't think that particular calculation is very useful. It would be nice, it was nice, in fact it was done, to show that this argument that I've been hand-waving about, that these terms don't show up, actually is realized when you do it, you actually do the calculation. People have done this. So it's an exercise that you solve. Whether the results are of great interest phenomenologically is more questionable. Now there's another approach where this is actually not true. You can imagine knowing the underlying theory. You know what is called the ultraviolet completion of the standard model. That means new physics. You know the new physics. And so at some scale, you would be able to see all this, new world. It's right here, the new world. You know it. You know what it is. You know it here. It's, it depends. If you're in the 1980s, it's a grand unified theory. It's right here. Okay? And here you have the standard model. And in between, you have the effective theory. The effective theory can be made to work all the way almost to the scale of the heavy guys, but not beyond. Okay? So what you can do is say, okay, I don't want to deal with the grand unified theory. I just want to deal with my standard model effective theory. So I can match the true theory to the effective theory at a scale that of my choosing. So I can say, what do I mean matching? Well, you calculate a bunch of observables using the effective theory, and you calculate the same observables using the full theory, and you make sure that the results match. That's what it's called matching. In the process, the coefficients of the effective operators are expressed in terms of the parameters of the underlying theory. They're no longer arbitrary. They depend on the parameters of the full theory that explains the universe. Very nice. Why would you want to do that? Well, maybe effective theory is more convenient. Maybe nobody has written the right MATGRAPH files for the grand unified theory that you know is true, but everybody has written them for the effective theory that's below. Maybe just a practical thing, that kind of thing. All right, you can match them at any given scale. You can match them almost at the grand unified scale, or you can match them below. If you match them at a very high scale, grand unified scales are large, 10 to the 16 GeVs and so on. Our experiments are at 10 to the 3 GeV. So if you match them here, you really want to do the evolution of the coefficients. Now, this is the effective coefficients from that very high scale to the LHC scale. You really want to do that because the energy gap is humongous, right? Okay, so that in that case, doing the running is very useful. You match at a high scale, and you run the coefficients to the scale of interest to experiments. And that's fine. You could also match at the LHC scale. That's also possible. Fine. Okay. In which case, doing the running, it's not very useful. If you match at 3 TeV, LHC is at 1 TeV, doesn't move. This effect, the changes induced by running are very small, unobservable. So, but in that case, if you match at a very high scale, it is useful to know how the coefficients run. But that is a very specific situation. I'm telling you, you already know how the universe looks. The question of what is under the standard model has been answered. And, you know, doing an effective theory which is designed to talk about situations when we do not know the underlying theory, you know, it kind of loses interest. We already know the underlying theory in this scenario. And so you might imagine situations where the underlying theory becomes apparent at a very high scale, in which case then the running from low scale to that very high scale it will be significant. On the other hand, since you don't know what's beyond that very high scale, I mean, you just run the coefficients and you just finish. You know, there's no physical content there. And so the running of these guys within the EFT is not very interesting because the effects are small. The running becomes interesting when you go from this top-down approach in that case. But in that case, you have much more interesting things to do. That is, understand the underlying theory, which is the true expression of nature, not the EFT. Any questions?
Sir,
Yes?
so in one of your slides you have written SO8. So is it same as SO8?
SO8, yes. I'm sorry. A and V are the same index. Sorry, it just I used to label the vertices, and I changed. I apologize. Sorry. Yes. Sorry. Other questions? Okay. So again, this exercise was made to show that the EFT is compatible with the loop expansion, but disappointingly perhaps, I've also argued that doing the calculation is not as interesting as one might hope. Since I have a few more minutes, let me begin with the next topic, which is much more useful. Much more useful. I've been arguing, and this is much more useful for the case where the underlying physics is weakly coupled. I've been arguing that in that case, the appropriate expansion as expressed by the index S will be in powers of 1 over lambda. Large power, small effect. Small power, larger effect. But in fact, we can refine that. We can refine that. Because some of the operators, as I will argue, some of the operators that you face are necessarily loop generated. So the coefficient that is independent of the type of new physics that, well, I'll qualify that. If the new physics is a version, completely arbitrary version of a gauge theory, that is a theory composed of fermion scalars and vector bosons, but without any further specification, then there is a group of operators that are always generated by loops. They cannot be generated at tree level. And that is important phenomenologically because the coefficients of such operators are then suppressed compared to the coefficients of other operators. And so those operators have small effects in themselves. And so you want to look at them, fine, but you have to be aware the effects that they produce are going to be suppressed compared to the effects of other operators. Unfortunately, many of the very interesting operators, those that produce could produce significant deviations from the standard model, are the ones that are generated by loops. And though it might look at first sight that they generate significant deviations, they do not because of the operator itself, but because its coefficients necessarily have a suppression, extra suppression factor beyond the power of the scale. And that's what I'm going to talk about today in a minute, in the following. Oops. Okay, So let me make a definition. Oh, okay, so this is the kind of thing. So let me make a definition. Suppose you have an operator that's generated at tree level. Then the coefficient by some underlying weakly coupled decoupling underlying new physics. The coefficient then will be expressed in terms of the coefficients of the underlying theory by an expression of this form. If the operator is generated at L loops, you have a similar form, except there is a suppression factor, which, as I mentioned here, is so strong that makes this effect, the effects of this type of operators, unobservable. My point is that these guys are phenomenologically more interesting than these guys in most situations. There are exceptions, and I'll mention one, but in most situations, this is the thing. These guys provide the best window into new physics available to us. So here I assume, as I mentioned earlier, that the standard model extension is, that is the underlying physics, is a gauge theory. Beyond that, and it's a field theory, okay, that is, has local interactions. Beyond that, I will make no assumptions. Then I will argue that there's a set of operators that are always loop generated, always. And I will call them loop generated. The remaining operators may or may not be generated at tree level. So that means that there's certain kinds of new physics where these remaining operators are in fact generated at tree level, and there's other kinds of new physics where they are not generated at tree level. And I will give examples of this possible duality also in a minute. Since they may be at tree level, I call them PTG operators, potentially tree generated. To find these guys, I will need the allowed vertices. So I am going to assume the underlying theory is some gauge theory with a bunch of scalars and vectors and fermions, okay, completely general, that contains a standard model. Okay. And I am going to look at the tree-level graphs. This will be a constructive proof. In doing so, I will assume that there are no mixings between heavy and light fields. That is, there's no term in the Lagrangian that are quadratic in the mixing. What I mean is there is no heavy scalar times light scalar term in the Lagrangian. There is no light fermion times heavy fermion in the Lagrangian. If you have those things, the problem is that the mass terms are then mixed. Right? If you have a I will do this as an example for scalars. So suppose you have a scalar little phi that you say is light, and a scalar big phi that you say is heavy. Well, by this you mean roughly, and I don't want to be as very careful, that the Lagrangian has terms that goes like little m phi squared, big M phi squared, and that little m is much greater than big M. But if I add a mixing term, okay? Yes. Thank you. Other way around. M, thank you. But if you add a mixing term, this thing becomes now more murky. If you want to identify what the heavy modes and what the light modes are, you must diagonalize the mass matrix. The mass matrix is m squared, yeah, mu squared. That's the mass matrix, right? And you want to diagonalize it. It will have, in general, a light mode that is a large eigenvalue or an eigenvalue much larger than the other one, following this hierarchy. But the eigenvector corresponding to the light and heavy will not be pure phi, will not be pure capital Phi, will be a mix of those two. And so it will be a mix of this and this that will be the light one, and the orthogonal mix will be the heavy one. I mean, that's fine, you just do it, kind of thing. But when I say there's light modes and there's heavy modes, I'm assuming I already did that. And so I can tell you ab initio, these are the light modes. If I had, for some reason, some mixing term, I already diagonalized my mass matrix. I already identified who's light and who's heavy, and then I'm done. There will be no such terms. Not in the sense that there will be no terms because they're forbidden. It's because I already dealt with them by diagonalizing this matrix, identifying what's heavy and what's light. So these terms are not there. Again, let me emphasize, not because they are forbidden, but because I eliminated them by taking appropriate combinations of the fields. And I need to take those appropriate combinations in order to identify what's heavy and what's light. Otherwise, I don't know. Otherwise, the phi that I call light, in fact, has a component of a heavy field. It's no longer light. So this is what I mean by this light column. Exactly. Yeah, exactly. So what I'm trying to say is when I say there are light modes and there are heavy modes, I mean there are light modes and heavy modes, and at least at tree level or at the very basic non-interacting level, I already ensure that's the case. There's no ambiguity in it. Okay? By diagonalizing all mass matrices. Yes, exactly. Yeah, and so there's some linear combination of little guy and big guy that will have a small mass, and another combination, the orthogonal one, that will have a heavy mass. Okay. And so that's good. All right. So now.
We have some time.
I have 9 minutes.
Yeah, exactly.
Are you bored?
No.
Are you bored? No. I think I have some cartoons in the following.
Oh.
Okay, so, okay, I think, right. Let me just set up the notation and then we'll stop because it's been a heavy load for the moment. The reason I don't want to just completely stop is I do have some phenomenological applications for tomorrow. So today is mostly formal, and they're very much crammed into a lecture, and I want to have a little bit more time also. So I want to not stop completely now, so I'll have a little bit more time later. Okay. All right. Since I told you that the underlying theory, which is weakly coupled, is a gauge theory, it will have gauge fields. The full theory, gauge fields, I called V. And it's composed of two types of gauge fields, the light guys that I call A, and the heavy guys I called X. Okay? V is all of them light and heavy. And the Lagrangian contains a kinetic and interaction term of the V's of this form, as any gauge theory does, where V mu nu A is the standard field strength tensor. There are some generators associated with the adjoint representation of the gauge group, which I call TL, T1, 2, 3, 4, 5. These are the generators of the group, or the members of the algebra of the group. Now, inside this group, the standard model group must be. There must be a subgroup of the full group, whatever it is, where the standard model group lives. In all grand, you can check that in all grand unified theories, you can find a subgroup that's SU2 cross SU3 cross U1. Always, always, always. I'm not assuming that the full group is simple. That is, it's not like SU10, SO10 or SU5 necessarily. It can be something else. It can be whatever the SU4 times SU4 or something like that. It doesn't have to be a simple group. It can be any group kind of thing. But somehow inside it, there must be some combination of generators that correspond to the standard model gauge group. Those close into a subalgebra because it is a group inside the other group. And so the commutator of two of those corresponding to the light gauge bosons, which are the standard model gauge bosons, would be the standard model guys. The generators associated with A, that I call light generators, must close into a subalgebra. So the commutator of two of them must give you another of them. This is not to represent an index. It just said the commutator of a light with a light gives you a linear combination of light guys. They will not give you any terms that have heavy guys. Another way of saying it is that the structure constant of the group that contains two light indices never have a heavy index beyond. So you can have an F with 3 light indices. You can have an F with 1 light index and 2 heavy ones. You can have a structure constant with 3 heavy ones, but you cannot have 2 light and 1 heavy. It just doesn't happen because of this condition that the light generators close into a subalgebra. And so based on this, I can find out from all the terms that show up here, which are allowed and which are not allowed. You're not supposed to remember this. Trust me, this is correct. So the cubic vertices are proportional to the structure constant. The quartic vertices are proportional to a contracted product of 2 structure constant. And you can see from what I just mentioned here that these quartic vertices are allowed. Others are not. In particular, you see no vertex that AAX. There's no vertex like that. In fact, you can see, and so and that in fact will turn out to be useful. And this implies, in particular, that certain pure gauge operators that made out of pure gauge fields are necessarily loop generated. This is the term in the Lagrangian that generates cubic terms in the gauge fields at tree level. There's no other one. This is it. Okay. And so you have if you have an operator like this that has 3 light generators, we will see later on that it's necessarily loop generated. We will see in a minute. Okay. So let me tell you, since I'm about to run out of time, let me tell you what's going to happen in a little bit. Okay, I'm going to use this argument such as this, just looking at the structure, general structure of the underlying theory to find what vertices are allowed not only in this type of terms in the Lagrangian, but also in those involving scalars and fermions. So you will see down the line lists like this involving scalars, involving vectors, here involving vectors, but later on involving scalars and fermions, which those that are allowed, those that are forbidden. And from those, since I know now the vertices that are allowed, I can check which ones actually can, I know the vertices that are allowed. I can find out what graphs, what tree-level graphs occur. And from those, I will find out which operators are generated at tree level. So it's involved and it's formal, but I think it's a useful exercise to at least see it done once, even though it's not in full detail. Okay? I'll see you in the afternoon where I'll complete the proof. Thank you. Again, I can't.
Heavy and one light index, why it is not there? I mean, in your list of cubic terms.
Oh, why don't I have light? Yeah, light.
Light heavy.
Okay. The reason that happens is, I'm going to write on the board. Okay. So the question is, again, why no light guy? Explicitly is the following. Oh, I want this. But I can recycle this. Okay. So you have the general V mu nu. I'm not going to write in full detail. Okay, but looks like a derivative term plus a term with f and two v's, like this. All right. So this has an index A, Here's A, B, C, B, C. I'm not going to worry about the Lorentz indices at all. Okay. So I'm going to take the Lagrangian has a square of this guy. Okay. So V squared, V mu nu, has several terms. Has the quadratic term, roughly. Okay. Has the cubic term. And has a quartic term. Same A, C, D, E. Okay? Okay, I just took the square of this, and this, I'm not worrying about factors of 2 or anything like that. Okay, because the light generators close into an algebra, what it means is that in general you have this expression, TA, TB, and I'm taking the Hermitian here, it's I, F, ABC, TC. This is for general indices. Now, because they close into an algebra, the light generators, T, A, L for light, and T light T1, light 2. Okay, these guys are some of these guys. Some of the TAs are the light generators. So for those you have I, F, L1, L2. I'm just doing C, TC, the general case. But because they close into a subalgebra, the commutator will necessarily be a linear combination of the light guys only. Okay, so it's I, F, L1, L2, L3, T, L3. There's no heavy guys here because they close into an algebra. And so you can see that if you had a term that was AAX, okay, you have AAX or AAX. 2 indices are light indices because the A's are the light guys, and the other one would have to be heavy. But that never happens. You only have light, 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 You never have light, light, heavy. And that is the you never get AAX or AAX or XAA. It doesn't happen. Okay? Other question? Okay. All right. Then we can go to tea. Thank you. Thank you.
Okay, so let's start. So today I'm going to talk about dark matter and the applications of effective field theory in dark matter physics. And first few slides, I mean, as many of you are working on this field, so for some of you maybe some part of the things that I am talking about is redundant, but maybe there are some interesting things that you can borrow from this talk also. I mean, particularly those who are explicitly not working in this area. Okay, so the whole thing started with the effort of Fritz Zwicky, who was studying the radial velocity dispersion of galaxies in coma cluster around 1930s, and this is the famous picture that is usually portrayed for Fritz Zwicky. I do not know whether it was after he found out that okay, there are missing masses or something, but this is the picture that you always get. I mean, if you type Fritz Zwicky in Google images, this is the first picture. Okay. Now what he was doing is something interesting. So he used virial theorem. So all of you know what is the second law of our famous classical Newtonian dynamics, and what you can do that you can rewrite this equation in this way, where you have half of d2 dt2 mi ri square, that is equal to ri dot fi plus mi dri dt whole square. It's a simple step. Now when you take the time average, then you know this big line on top of the head is essentially the time average that I am taking here, or rather he took there. And then if you assume that the more or less the velocity distributions of the galaxies in the cluster remains the same, the left hand side actually goes to 0. So this vanishes. So what it gives, so this quantity ri dot fi taken as a time average is called the virial. So this is actually twice into the average of kinetic energy, right. So half mv square is the kinetic energy. So this virial is minus 2 kT bar. Now if you want to calculate this virial ri dot fi averaged, this is simply, you know, in a gravitational potential we all know that this is g mi mj by rij, and one can calculate this quantity, and so therefore this indicates that this mi vi square averaged will be sigma I, sigma j less than I. These are the sum over the galaxies, you know, you are calculating the interaction between different galaxies in the galaxy cluster. Now this quantity can be calculated, this is not very difficult. Actually in PH 102 course we do this calculation, right, that what exactly this will be the this will come out, and if you do that calculation assuming a uniform density of galaxies within the galaxy cluster, this will come out to be 3 by 5 g m total square by r total. So this m total is the total mass within the galaxy cluster, this r total defines the total radii of the galaxy cluster. This m total is of course the same thing, which I am replacing from this term on the left hand side, and this is simply, so this sum over the indices means repeated sum over the indices means sum of all the i's. Okay. So therefore mi vi square, which has implicitly sum over I and then average, you can simply replace that as m total v square bar, and which can be written in terms of 3 by 5 g m total square by r total. Now what it does, that it actually allows you to write this average velocity of the galaxies within the cluster in terms of the total mass which is contained within the galaxy cluster. And if you use this v square bar of the order of 10 to the power 15 centimeter square per second square, this is roughly the observed velocity distributions of the galaxies within the cluster along the line of sight. Then you infer what is the M total which is contained within the galaxy cluster, just using this relation. And then on the other hand, what you can do, so this is the calculated one, M total, using this relation, which is something like 4.5 into 10 to the power 13 solar mass. Whereas you can also infer what is the total number of galaxies within the galaxy cluster from your observations, and that turns out to be something like 8.5 into 10 to the power 7 solar mass. So clearly these two things were not matching. There is a discrepancy in what you call the missing mass, and this was sort of postulated or attributed to the presence of some non-luminous matter in the galaxy cluster, which he called Dunkel Materie in German. His paper was in German, so not many people actually did read that. But this was the first effort of kind of identify the presence of some non-luminous matter within the galaxy clusters. Followed by this, there were several observations. This was very popular around 1970s. Vera Rubin actually was studying the angular motion of the galaxies in the galactic rotation curves, and this is something that we all know, that when we go from the center of the galaxies to the outside, the rotational velocity should fall off, as this is what is called the Keplerian fall, that V should kya ho gaya? No? Okay, so it should in principle fall off as you go outside the galaxy cluster. The rotational velocities of the galaxies within the galaxy cluster as you go out. But on the other hand, what was observed was something like this in this green curve. So there is once again a discrepancy between what you have observed and what you sort of infer. Is it because of stepping on the wire here? Okay, okay, I better be careful. Okay. So this was another observation which actually was in favor of postulating the presence of some non-luminous matter. And then there was this observation later around 2006, which was via this Bullett's cluster, where you see the merger of two galaxy clusters. Now this part in the pink was actually the observation, whereas this parts in these two blobs was not observed, but it was inferred from what is called the weak gravitational lensing, which basically says that there is an invisible part of the mass in the galaxy clusters which actually sort of passed by each other without affecting too much. And this was also attributed to the presence of some non-luminous matter in the universe. And there was another support from cosmological observations, that when you look into the anisotropic CM and you infer, you do the simulations to describe this pattern, then there is a very funny thing that happens, that you conclude that your universe has ordinary matter which is only something like 5%. There is a huge amount of dark matter like 26.8%, and there is a big amount of dark energy which is even something more complicated, which we also do not know, which is almost like 70%. And this huge amount of dark matter that is present in the universe is also termed in terms of what is called the relic density. Omega is the cosmological density, this small h is the reduced Hubble constant, this omega h square is of the order of 0.1199 plus minus 0.0022. Now this inference was drawn by, I think, two successive experiments. One was this WMAP, and then there was Planck, which roughly predicted the numbers in the same ballpark, saying that there is some missing mass in the universe which is present, which we need to worry about. And the inferences, particularly from the cosmological side, was due to this person Peebles, who was awarded with a Nobel Prize in 2019. Now, if there are dark matter particles, then what can be they? First of all, if the particles are dark, then they must be electromagnetic charge neutral. The second thing is that because our observations are actually happening now, so they must be stable. So whenever they were produced in the universe, they have not decayed away, they are present now. So the stability is another aspect which we usually assign, and they must be massive, because all these effects that we have seen for the support of their presence are via gravitational effects only. So there are two main mechanisms to produce dark matter. One is what is called the thermal freeze out, and the other what is called non-thermal freeze in. And there are many possible particles that you can think of within this paradigm of thermal freeze out. The one that I will be mostly focusing is what is called weakly interacting massive particle, or WIM. There are efforts like thinking of something like strongly interacting massive particles, or same strongly, however this strong interaction does not refer to the interactions with the visible sector, but within the dark sector itself. And then there is another way of postulating how the dark matters acquired the correct relic density in the universe, by saying that they were not in the thermal bath, but they got produced via some feeble interactions out of equilibrium, and that is how they are termed as FIMP, feebly interacting massive particle. And of course, I mean, these are some broad characteristics that you have assigned for the dark matter, but if you want to come up with a particle which fits the bill, there are many options that you have. And also in terms of the mass of the dark matter, there is a huge range. I mean, where in this region between few hundred GeVs to TeV, but one is always okay to go to the light dark sector or heavy dark sector, I mean, depending on what kind of model that you want to consider. So now I will just quickly sketch the process of thermal freeze out. Now the number density of any particles in the universe, in the early universe, is evaluated via this equation which is called the Boltzmann equation, because this takes care of the number densities of the particles which comes from their interactions in an expanding universe, and that is what this equation shows, that you have this number density of the dark matter plus 3Hn is equal to minus sigma v to n psi into n psi bar into n psi equilibrium minus n psi bar equilibrium, something like that. And you do recast them in terms of co-moving volume. You define an yield y, which is actually number density by the entropy density, and the variable instead of time in terms of dark matter mass by the temperature of the thermal bath, and then this equation looks like dy dx etc. This 3Hn term actually drops. So this is the one that usually people solve in order to get the relic density or the freeze out point of the dark matter. So basically there are two regimes. You can say that one, when the rate of interaction was much larger than the expansion, and then the particles, dark matter particles, were in thermal bath or in equilibrium, having this equilibrium number density. When the rate of interaction falls below the Hubble expansion rate, then there is a freeze out which occurs. And if you solve these equations, there is a generic pattern which is shown via this y versus x curve. So this is the falling distribution, the equilibrium distribution. The dark matter was having the equilibrium distribution at the early universe, and there was one point where it could not match up with the expansion and freezes out, and that gives you what is called after the freeze out, it gives you the relic density, which you now need to match from the observation of omega h square equal to roughly 0.1. So if you solve the BQ, particularly for this kind of WIMP like cases, very roughly saying, this omega h square turns out to be something like 2.4 into 10 to the power minus 10 GeV to the power minus 2, the annihilation cross section of the dark matter to annihilate into the standard model bath. Now this shows something interesting. It says basically that if omega h square has to be, so for this freeze out mechanism to occur, for the dark matter freeze out, the relic density is inversely proportional to the annihilation cross section. And the second point is that If you have to get omega h square of the order of 0.1, then you see that this sigma v has to be of the order of 10 to the power minus 11 GeV to the power minus 2. So this number is something that we know. This is the strength of weak interaction. So therefore you say that when the dark matter has roughly the strength of weak interaction cross section with the visible sector, then they give you correct relic density, and this is why this kind of particles are termed after weakly interacting massive particle or WIM. And in the second possibility, I will briefly say that when you have a non-thermal freezing, you basically postulate that the interaction between the dark matter and the thermal was not good enough to keep the dark matter in equilibrium. So therefore, what you have to do, so it follows from the same Boltzmann equation if you wish, and but on that particular case, what you do not have is the reverse process. So you only have the production of dark matter from the thermal bath via scattering or via decay, whatever that you wish. And this produces this kind of a curve. So you start with number densities which are close to 0, and then you slowly accumulate the dark matter number densities as you go along, and at one point of time when the bath of the universe drops below the mass of the dark matter, you cannot produce them more, so then they saturate. So this is the mechanism of what you call the freeze-in mechanism. And unlike the freeze out, where it is inversely proportional to the annihilation cross section, the freeze-in mechanism basically suggests that the dark matter number density or the yield is proportional to the production cross section. So therefore it is proportional to whatever the feeble interaction strength the dark matter has with the thermal bath. So this is the difference between these two, and roughly once again, if you want to adhere to the correct relic density, the freeze-in basically predicts the coupling of the order of 10 to the power minus 12, where the for freeze out you can take this lambda of the order of 1. I mean, this is just a rough sketch. Now the question is when we can detect the dark matter. The point is, if the dark matter is a weakly interacting massive particle, then this strength of interaction like lambda prime, which causes the correct freeze out and creates the right relic density for the dark matter, is actually conducive for the dark matter to show up in earthly detectors, like in direct search and collider searches, which we will talk about. Whereas for the freeze-in mechanism, because this lambda is very, very tiny, it is difficult unless you take some very special cases of seeing their signals. So this brings me to the search strategies of WIMP in particular. There is one kind of search which is the direct search. Basically you assume that we are moving in this WIMP soup, and then WIMPs are coming and hitting us from everywhere, and then we have to choose our detector so that the dark matter scatters off the detector, and depending on the mass of the dark matter, it can rip off the nuclei or the recoil the electron from the outer orbit, and it can give nuclear or electron recoil, which produces a scintillation which you can observe. So this is the picture of a xenon detector. On the other hand, you can also look for dark matters in collider searches. For example, Large Hadron Collider is running, so you can produce the dark matter pairs at the collider due to their interactions with the visible sector. And then there are also indirect search possibilities, that in the dense region of the galaxies you can also have the dark matter annihilating to produce particularly the antiparticles, because antiparticles are not quite abundant in nature. So if there is an excess of them, then you can actually attribute to the presence of a dark matter also. Yeah, so hard photons and antiparticles in the high dense regions in the galactic center. So before we proceed, we must say that from all these observations we have no confirmed dark matter signal yet. I would like to devote one more slide on, actually two more slides on collider signal of dark matter. So this is a cartoon which I copied from Tim Tate, and he basically shows that there are mainly two possibilities of producing dark matters at collider. In one case, if your dark sector is not extended, then you have to directly produce the dark matter, but because the dark matter misses the detector, you do not have an observable, right, because the dark matter is electromagnetically charged neutral, so they do not show up. So what you have to rely on what is called the initial state radiations from the colliding particles, and that will give you a possibility of seeing some visible particle along with missing energy, and this is something what is generically termed as mono X signal. On the other hand, this possibility is more optimistic one, where you say, okay, you have an extended dark sector, you have heavier particles belonging to the dark sector, which eventually decays to dark matter in association with some leptons and jets, and that gives rise to what you call multi-lepton and multi-jets. Now, these missing dark matters, what do they produce? They actually give you some variables by which you can probe their presence in the detector, and one of these is called the missing transverse momentum. I will explain that in the next slide. So, missing transverse momentum is essentially defined by the transverse momentum, or rather sum of, so this lepton, jets or photons, whatever that are there, if you take the summation over the x component of their momentum, square it, do the same for the y component of them and take a square root. This is what defines the missing transverse momentum, although very commonly people say this to be a missing transverse energy, but as you can see that it is in principle a momentum. Now, there is another variable that you can define, which is the missing energy, and this missing energy can be defined by simply the visible energy that you actually found out associated with the particles that you produce in the collider, like lepton, jets and photons, etc. You sum them up, subtract from the center of mass energy to define what is the energy associated with the particles which have missed the detector, and that is what is called the missing energy. And you can also define a missing mass, so which is like sum over I pi in the initial state minus sum over f pf, the particles which are visible produced in the final state. Do take a square of that, and that is what is attributed to be missing mass square. So, these are the key variables that you can actually assign to see the presence of a dark matter in the detector. Now, the point is, for this missing transverse momentum is useful for those kind of colliders where you do not have an access to the center of mass energy at which this collision is happening. Like in context of LHC, you know the proton colliding center of mass energy, but you do not have the access to the sub-process center of mass energy. So, constructing missing energy or missing mass is not possible in those kind of colliders. These are useful for ILC, FCC or muon colliders. Whereas, missing transverse momentum can be defined in context of any colliders that you want to study the presence of dark matter. And of course, this is a class of signal of dark matter, but there are many other possibilities, including disappearing charge track, displaced vertex, so on and so forth. Yeah, I will not go into the last this thing. Okay, so I just wanted to do one quick exercise just because this is a school and many of you of course know it, but I just wanted to show how this missing transverse momentum can be constructed in context of a mono X signal. So, you know, these are some Feynman graphs by which you can have monophoton or monojet along with the dark matters produced in the collider, and where this X can be anything, as I just mentioned. Now, what is this missing transverse momentum? So, consider a collision like AB going to C plus D plus E, where C is one of these radiative particles from the initial state and D, E and E are the dark matter particles which are produced. So, this is your XYZ coordinate, and you assume that these are the AB initial particles which actually collide and produce C, D and E. And this D and E having this specific color indicates that they are the particles which are not detected in the detector, I mean they are the dark matter. Now, the definition following what we wrote in the last slide, the missing transverse momentum is basically Pxd plus Pxe whole square plus Pyd plus Pye whole square, correct? So, this is the x component of d and E added together squared, and the same for the y component and squared. So, this is the definition of missing transverse momentum. Now, you will say that I do not have access to the Pxd and Pxe or Pyd and Pye because these are associated with the particles which does not get detected in the detector, right. So, these are the particles which are invisible, which escapes the detector. Now, the question is how to measure them, but now you have to remember that we are assuming that the collision is occurring along the z direction. So, this basically means that you have the momentum conservation in all the three directions. So, I am particularly writing this along the x and y direction. So, Pxe plus Pxd plus Pxe has to be equal to 0, right, and so therefore, the Pxd plus Pxe, this quantity can be written in terms of Pxc just from the momentum conservation, and the same thing happens for the y component, that Pyd plus Pye is nothing but minus Pyc, the momentum associated with the visible particle. So, therefore, you can simply say that this missing transverse momentum is essentially square root of Pxc square plus Pyc square, or rather the transverse momentum of the visible particle which has been produced. So, therefore, you have access to the missing transverse momentum even if you do not know the subprocess center of mass energy. So, this is a quintessential variable with which the dark matter has been searched so far. And you can extend this idea for the richer signals which I talked about, where you produce also the leptons and jets along with this dark matters and missing energy. So, the exercise straightly you can extend to that case also. But once again there is no signal excess confirmed so far, but the searches are going on. Now, I will come to this point that how effective theory can help us in studying dark matter physics. The first point is that because there is no standard model particle which mimics the characteristics of dark matter, using SMEFT it is very difficult to actually probe the dark matter standard model interaction. So, there is not a great possibility of getting a dark matter from the construction of SMEFT that we have been talking about. So, what you actually have to do, that you have to assume the presence of some dark matter particle and construct the operators which have this kind of an interaction, dark matter standard model interaction, and depending once again on the mass dimension you have to appropriately adjust by the power of new physics which generate that kind of interaction. I will give you an example as I go along. So, this operator is invariant under the standard model symmetry and the dark sector symmetry which you usually assign, and it should be Lorentz invariant at the same time. And most often what we do, that for the simplicity, because we do not know what is the symmetry that governs the dark sector. Now, what do we require a symmetry to be there in the dark sector can be answered in the following way, that the stability of the dark matter is something which tells us that the dark matter particles should be having some symmetry which there is no lighter particle than that obeys. Okay. So, it is kind of saying that the electron is the lightest lepton in the standard model because of the lepton number conservation, and that is stable. So, similarly, the lightest particle which transforms under the dark symmetry must also be stable. Okay. You can have heavier particles, but the lightest particle which obeys this symmetry must also be stable. So, therefore, we assign a symmetry to the dark sector particles also. In most of our exercises, what we do, that we assume that the standard model particles do not have a dark sector transformation, the transformations under the dark sector symmetry, and vice versa, that dark sector particles do not have a transformation under the standard model, but this is a very loose statement. you can construct n number of possibilities where this violates this particular simplified assumption. So, in general you say that what we are interested in is actually in this dark matter standard model interaction, because that governs the freeze out and gives rise to the relic density associated with the dark matter, whereas at the same time that also dictates the detectability of the dark matter in earthly experiments which people are looking into. So, let us talk about the simplest operator that can give you an interaction between the dark matter and the standard model. So, the first thing that we have to think that whether we can write a renormalizable interaction at dimension 4. Now, if ODM OSM has to give rise to mass dimension 4, we can divide it in half and half, like 2 mass dimensions for the scalar particles, standard model particles, 2 mass dimensions assigned for the dark matter particles. So, there are only 2 standard model gauge invariant operators which are of mass dimension 2, and that one is h dagger h or phi dagger phi in our previous notation, where this phi or h is our standard model Higgs isodoublet, and then other guy is this b mu nu, which is the U1 hypercharge field strength tensor. So, both of these are actually gauge invariant mass dimension 2 operators. So, the simplest way that you can write a dark matter standard model interaction is by stitching a scalar like phi and say that this is h dagger h phi square. Of course, you have to assume that phi is a scalar singlet, does not have a transformation under standard model gauge group, and this is what goes against the name of popularly known as Higgs portal interaction, because the window with which this dark matter interacts with the visible sector is this Higgs interactions. And the phi is a dark matter, provided of course it possesses no electromagnetic charge. Once you remember that famous equation that we wrote, that q is equal to T3 plus y. So, therefore, if you have the dark matter which is an isosinglet, there is T3 is equal to 0. So, the simplest thing that you have to do is to assign a 0 hypercharge to the phi, and then that gives you a viable Lagrangian. Now, one more thing that you want to do here, that you assign a Z2 symmetry for the dark matter under which phi goes to minus phi, and then you have a Lagrangian. So, then you can say, okay, I allow phi square h dagger h, but in that same process I cannot write a term like phi h dagger h, this is disallowed by the Z2 symmetry, and this also forbids the decay of the dark matter into the standard model particles. Okay? And then you have the Lagrangian and a model for a dark matter particle to give rise to the right relic density. Now, you can extend this whole idea to operators beyond dimension 4, and once again here the GSM that you assume is the standard model gauge group, and this is the list of operators which I am copying from Jose's paper, and he is going to perhaps talk a little bit more on this part. Here once again, because I am copy pasting, so never mind, I mean this notations, this mod phi square, this small phi that you see is actually the dark matter. This capital phi is the Higgs isodoublet, okay? And this is the operator that we just talked about, okay? And similarly, in dimension 5, you can have this phi square with a cyber psi. So, this opposite. Yeah. This is the isodoublet. The small phi's are the standard model isodoublet. This capital phi's, because they are bold, they are dark matter. They are more darker. Yeah. So, and this size, for example, here they are also, yeah, this is an example of a fermion isosinglet. You also assume a fermion, but cyber psi has a mass dimension 3. So, cyber psi mod phi square is also an example of Higgs portal interaction via a fermion dark matter, but that has to be suppressed by a scale of lambda. Then you can say, okay, all right, I want my dark matter to be stabilized not under a Z2 but under a Z3. So therefore I can have a term which is like phi cube. Okay? And so therefore I can have an operator which is like phi cube mod of phi square. So this is also an example of dimension 5 effective integral. Yeah. Vector like fermions, singlet under standard model and so on. Yeah. They do not have any transformation under the standard model anyway.
No, but from the priority point of view.
Yeah, exactly.
They are not vector like internal calculation.
Correct.
Are there experimental constraints on if dark matter can be scalar or spinor or tensor?
No.
But if we go beyond scalar, then for spinor it will be 3 by 2 mass dimension.
Exactly. That's what I was saying. That
Then, if you want to keep standard model fields, then you have to go above 6 times.
no. It's in dimension 5. So why do you have to go to mass dimension 6? Psi bar psi mod phi square is an allowed term, which has mass dimension 5. Mod phi square is your h dagger h. And you stitch a psi bar psi as it's a vector like fermion, singlet under the standard model, 0 hypercharge, stability is ensured because you want psi to transform like minus psi under Z2, you are done. Whether this is phenomenologically viable, it's a different question. Now I can give you examples where you can write renormalizable interaction with a fermion dark matter, but that will require more field. If you just have one fermion dark matter transforming under a Z2, this is the simplest operator that you can write. And similarly, you can go through this list and find out the other interesting operators. I will talk about one possibility. So remember, I introduced this B mu nu as one of the gauge invariant, standard model gauge invariant mass dimension 2 operator, right? But the problem is that because it has Lorentz indices, you at least require one x mu nu to actually cancel or rather nullify those indices or make it Lorentz invariant, so to say. On the other hand, if you just have a B mu nu x mu nu term, because x mu nu will be the field strength tensor associated with the dark sector particles, so in principle they will be able to decay to the standard model particles because they will only have del mu x nu minus del nu x mu, right? So they will actually have a mixing or decay with the standard model particles. So therefore, it is necessary that if you want to identify a vector boson dark matter in the simplest possibility, then you require another scalar at least, heavy scalar belonging to the dark sector, which has same transformation under the Z2, so that x mu nu phi is actually an invariant under Z2, and together B mu nu x mu nu phi is a GSM Z2 symmetric Lagrangian. Okay, so now so there is actually the effort started with this list of operators wrote by Team Tate, Rajaraman and his team. So where they identified all these operators, assuming that the governing symmetry is not the full standard model but actually the SU3 C cross E1 electromagnetic, and these are not very difficult to construct. I mean, because you just have to worry about the electromagnetic charges associated with them. You don't have to worry about whether they are left-handed doublets, right-handed singlets, so on and so forth. So this exercise was done by them, and similarly for scalars, for fermions, for vector bosons, they actually wrote this kind of possibilities. Now there is also an example of what you call the EFT to standard model approach. Suppose you have an operator, then you can also have a new physics which Joydeep also talked about in great details, like you can identify a full-fledged UV complete model which can generate that kind of an effective interaction that you are writing within the standard model, within the DMA EFT framework. For example, you consider this operator like chi bar gamma mu chi, q bar gamma mu q, okay? And what you can do, that you can actually assume the presence of a heavy vector boson which couples to both your quark sector as well as to your dark matter sector, and that can generate this kind of effective operator, and you can say, well, I am at energy scales which is much lower than this x mu, so therefore I can generate these effective interactions. Okay. And you can also set a limit on the scale of lambda to be greater than m chi by 2 pi if you assume the perturbativity of these two vertices like g chi g q is less than equal to 4 pi square, then there is a limit that you can set that it must be at least greater than equal to m chi by 2 pi. All right. So, while people actually talk about the effective operators, people also talk about the simplified models, assuming a mediator which mediates the interaction between the dark matter and the standard model vertices. Now, I would just briefly like to talk about some of these fermionic dark matter operators. So, I just inflated one of those terms like J mu Sm, J mu dark, which I wrote in the first slide from Hose's paper, and that will generate this kind of interaction. Like you can have chi bar gamma mu chi, L bar gamma mu L, gamma mu gamma 5, blah, gamma mu gamma 5, gamma mu gamma 5, gamma mu gamma 5. So, these are the lepton doublets that you have in the standard model, and these are the dark matters for you. Okay. And interestingly, this is something that you can actually, because we have defined what is Majorana and what is Dirac, so you can actually show that this kind of operators pertains to Majorana dark matter. And without assuming a, okay, so this is a comment, like for example, if you are interested in probing fermionic dark matter effective operators interacting with the visible sector, then in principle you should take all the operators together and do your analysis. So, I will just briefly talk about the how to calculate the annihilation cross section, because suppose you have this operator like chi bar gamma mu chi, q bar gamma mu q, and then you can simply write the Feynman amplitude to be something like, if you follow this notation, this is Vb bar gamma mu ua, this is a contact interaction, this is the simplest matrix element that you can assign to the presence of this kind of operator, which is of course suppressed by 1 by lambda square. And once you have that, you can do the matrix element squared and do plug in into the expressions of sigma v. Remember that here the center of mass energy has this v square by 4. So, 1 minus v square by 4 sitting downstairs, which will give you, when you write it fully, the sigma v, the annihilation cross section having terms proportional to v square also. There are terms without the v square also, and that is what is called the S wave contribution, but there are P wave contributions coming from this v square dependence, where v is roughly the relative velocity between the dark matter components. And then you can compute the corresponding relic density by taking the inverse of that and satisfying them to the observed relic density. You can use the same technique to compute the direct surge cross section also. What you have to do, that you have to rotate this diagram clockwise. So, then you have the direct surge graph, like this your chi is scattering off your detector, right, your quarks. And then you can simply replace your momenta like Pa going to minus Pa, Pd into Pc, Pd going to minus Pd. And once you do that, you can find out the spin independent cross section which comes out in this particular format. Now, there are some form factors associated with that for sure, and this particularly this dq, this small dq and capital dq, this will be now proportional to 1 by lambda square, because this is coming from the effective interaction. So, this part is a matter of little details, this is not very obvious and simple, but the matrix element square you can simply calculate via this process. Then you have to fold with appropriate form factors and so on to get into the dark matter nucleon level cross section, and then you match with your experimental observations and put limits on the dark matter standard model interactions. Yeah. And also, well, people talk about this spin independent and spin dependent cross section, there is one point to remember, that whenever the dark matter nucleon level cross sections can add coherently to the nuclear level, that is what is called the spin independent interaction. If there are spin dependent effects, then you cannot add them coherently. Okay? So, that is why the spin dependent interaction cross sections are way lessly constrained than the spin independent interaction cross sections. So, these are details that you can actually look into. There is one example which I thought that I will point out, given that Jose mentioned the renormalization group running of the Wilson coefficients. So, this is one example. For example, you assume that your dark matters do not talk to quarks and only talks to leptons. But then what about the direct search possibility of such dark matters? The answer is it can still produce the non-zero Wilson coefficients with the quarks when you run down them from the scale of Rayleigh density, where you assume the dark matters annihilating to produce produce standard model stuff and freezing out. From that scale, if you assume that these Wilson coefficients are matching, so so to say, and but experimentally what you have to do, that you have to do run these coefficients at the scale of the direct search experiments, which are very low, then this renormalization group running actually comes into play. So, I do not want to bother you with these expressions and so on, but this is something that people have done very elaborately. Now, if you do this simulations at the collider, so now as I said that you have two dark matters produced at the collider, and then you cannot simply produce the dark matters, you have to have a recoiling photon, Z, W, whatever, and with that you construct these variables like missing energy or missing transverse momentum or missing mass, the three variables that I talked about. Specifically for this particular vector like interaction operators, you see this kind of distribution. Once again, what bothers you is not the signal but the background, because you have a similar signal which is like mono X plus missing energy produced by E plus E minus to nu bar with a photon radiated from the initial state. So, this exactly mimics that monophoton plus missing energy coming from the standard model, which has way more interaction cross section than the dark matter signal. Now, if your dark matter operator, the interaction is produces similar distribution to that of the one that is produced by the background, it is very difficult to segregate. It is very difficult to segregate the dark matter signal from the corresponding neutrino background. And here actually we put some efforts and to identify a signal for two dark matter components to be present. The point is, once again, this peak in the missing energy or missing transverse momentum distribution is actually subject to, if you have extended dark sector, then this depends on the dark matter mass, the splitting of the parent particles that you produced of that one with the dark matter mass, as well as with the Lorentz structure with which the dark matter interacts. So, the basic point is that if you have then two dark matter sectors which are producing two different peaks at two different places, then the combined distribution may show a hump like structure and can give rise to a hint that maybe you have more than one dark matter component present in the universe. Once again, this has to be taken with the fact that this can be camouflaged with one dark matter signal and the standard model background. So, the question will be to segregate from that also. So, therefore, there are efforts to do that. I will not go into that, and then you can coin some statistical variables to identify how these peaks are segregated and what are the characteristics by which you can say, okay, they can really indicate the presence of two dark matter components, is a matter of details. But the idea is basically this simple. Now, this is another interesting point, which is basically that if you are focusing only on the mono X signals, then the Lorentz structure of the dark matter standard model interaction really actually affects the positions of the peaks that you actually get in the missing energy distribution. And this comes from the angular momentum conservation, collinear divergence, the operator structure in general, and then you have to choose an appropriate combination to see these two peaks coming at two different places. And as I said, that standard model background is often bothering. So, we sort of proposed to look into bin by bin signal significance distribution, which retains the shape of the distribution of the two peak distribution, if you may say, but at the same time, because if you just plot the signal plus background distribution, this kind of shape will be wiped off. Okay, so I just wanted to give you an example of constructing that operator B mu nu x mu nu phi from a UV complete model. Okay. So, let us assume that we extend the standard model with a U1x symmetry, because we wanted to have the presence of a vector boson dark matter, but at the same time this U1x symmetry, this gauge symmetry is broken. Keeping the Z2 unbroken will make sure that the dark matter is stabilized. So, therefore, you can have a scalar and you remember that I need an operator which is like B mu nu x mu nu phi, right, and where phi and x mu nu both have to be odd under Z2. So, otherwise that I cannot postulate an interaction between a vector dark matter and a standard model interaction. So, therefore, this is my goal. Now, here what I have, this x is the gauge boson under this U1x, where this S is the scalar which is actually the vacuum expectation value of which breaks the U1x symmetry. Okay. So, this is, and you can show from the invariance of this d mu x d mu s, sorry. So, the total Lagrangian, so the mx will be essentially gx into vs. So, this vacuum expectation value of S will actually break the Sm cross U1x spontaneously and giving mass to this vector boson dark matter. Given that V phi is equal to 0, the Z2 remains actually unbroken, and then you can write the full Lagrangian here. And then basically the situation is that your Vs phi, Vhs phi, where H is your isodoublet, S is the one which acquires the vacuum expectation value, has a transformation under U1x, breaks the U1x spontaneously, and this other guy phi which is transforming under Z2, but no transformation under SU this U1x, you can write the full scalar potential in this particular way. So, the situation is essentially that this S and H mixes after electroweak symmetry breaking to give you one heavy scalar, one light one. The light one you can actually assign to the standard model Higgs, while the heavy one you are not interested in. So, when you have this H2 very heavy and decoupled, that is the situation where from these renormalizable interactions you actually get to this dimension 5 effective operator which I just mentioned. So, because this H2 is no more there, the scalar which breaks U1x symmetry and generates the masses for the gauge boson is no more there. I mean, so then this gives rise to this effective interaction where this lambda and this can generate this kind of interaction of phi x and b, and once again from this interaction you can easily postulate that phi also have a Higgs portal interaction. So, therefore, that is in the thermal bath. So, that is present in the universe which can decay to produce your dark matter, and you can do a Friesen mechanism in this particular limit. Remember, this is an effective operator which is depicting the dark matter standard model interaction. So, one must obey this kind of a limit that this lambda must be heavier than m2, where m2 is the mass of this heavy guy which I have integrated out. This must be larger than the maximum temperature at which the dark matter is produced, that is larger than the reheat temperature, and greater than m phi and greater than mx. Remember, we have two degrees of freedom. We can also make x to be the dark matter or phi to be the dark matter depending on which is heavy, because the other one will decay to the other. Yeah, the heavier one will always decay to the lighter one. So, this gives you a possibility of looking into what is called the UV kind of a Friesen, where it is not slowly accumulated, the dark matter number density not slowly saturates, but it is actually saturated at the very high temperature, and this is a common feature with most of the effective operators giving rise to the dark matter relic density. So, this is also a interesting point. So, I think I will be finishing now, and before I finish I would like to point some of these issues, like when we are doing this dark matter EFT direct search, then this running of the corresponding Wilson coefficients may play an important role. The other point which I did not talk about is actually the validity of the DMEFT in context of LHC. You remember in yesterday's lecture we talked about that the validity of an EFT framework in context of LHC solely determined by the fact whether the invariant mass of the final state that you cook up is less than the scale of the new physics that you choose to expand the theory upon, right. Because otherwise if it violates the effective theory limit, then there is no point in doing that. The problem here is that when you produce two dark matters at the collider, like say for example LHC, there is no way that you can actually cook up the invariant mass of the final state, right. So, therefore, adhering to the effective theory limit for dark matter interaction or dark matter production at LHC is a difficult job. Now, people do it in different ways, saying okay, let us assume I produce them, only half of it actually contributes to the final signal. But excepting for doing some hand waving arguments, you cannot do it. There is no problem in addressing the ZH production with the standard model plus effective operator contribution, because you have two visible final state particles produced. You can construct the invariant mass, you can obey the effective theory limit. But for the dark matter production, it is difficult to do an effective theory in context of LHC. There are caveats to that, you know, but that is one of the main points, one of the points that I just wanted to mention. So, on the other hand, in colliders like future prospects like ILC or FCC, you have the full access of the center of mass. You know the center of mass energy. So, therefore, you know whether you are adhering to the effective theory limit or not. Okay. So, with that I will finish. Questions? There are no questions because everybody knows it. Yeah, JD. Yeah.
So, when you break the Z2 to this V,
No, Z2 I am not breaking.
even not through a symmetry breaking,
No,
you are keeping the
I am keeping the
so
Z2
that's why
real.
you are protecting the kinetic mixing.
We are breaking the U1x.
No, but you are protecting the kinetic mixing.
Absolutely.
Otherwise, you have kinetic mixing and then you
There is no Z2 breaking. So, the Z2 invariance makes sure that I only get operators which are like x mu nu, b mu nu, phi type.
sorry.
Yeah, go ahead. Maybe I take up the following question and then from you.
So, last comment that you were making about the these caveats regarding this LHC, I think probably it would be safe to have and that how much pattern momentum maximize you can have in the LHC.
Yeah.
And that could give a at least safe limit for the choice of lambda.
Yes, you can always take the lambda to be higher than 14 TeV, then anyway you are doomed because the production cross section will be 0. So, that is the caveat, yeah. I mean it will be very, very small. So, you can take that limit that your lambda is as heavy as 14 TeV, but then practically the cross section is so low, then it is very difficult to do any realistic phenomenology. Yeah.
Sir, first of all, thank you for such a wonderful talk.
Oh my goodness, thank you so much. I thought that deadly silence means that it was all obscure. Yeah. Okay.
Sir, can you please go to the slide annihilation cross section?
Okay. Okay. Direct search. Annihilation cross section. Right.
Actually, I have never done work in dark matter, so I am not expert. Sir, but I want to know, while calculating the matrix element here,
What would be the propagator and
There is no
and if-
propagator because it's a simplified model which I talked about. Like you have this dark matter scattering, you know, this one. If you are not happy with this guy, you take a simplified model. There is a propagator.
So does it always have to be in S channel, or can it be?
It can be T channel. Yes, it can be in T channel depending on what are the symmetry. In T channel there is a little bit of caveat because then we are going beyond that simplified assumption that OSM does not have a dark charge and the ODM does not have a standard model charge, because you have to connect one of the so this is SM to DM or whatever the other way around. But if you want to connect one SM and DM put together in one vertex, then you have to have this property that the standard models are also transforming under the dark symmetry, or either or both. So that's how S channel is simpler. I mean, that's the simplified model usually. Yeah, you have a vector current interaction, you assume a vector boson. You have the scalar interaction, you assume a heavy scalar, something like that. Yeah.
Thank you, sir.
It's not necessary that you have to ask questions. We can also break for lunch.
Sir, the missing energy figure which is comparing different experiments.
Not different experiments, the same experiments but different channels. Yes. Yeah, that's a horrible plot. Yeah, this one.
No, I just asked simple question like ILC, you said missing energy can be easily measured comparing to the LHC.
In LHC you cannot measure missing energy, but you can measure missing transverse momentum. That was my precise statement. And the second thing is that I don't know very well how to do a phenomenology of dark matter effective operators in context of LHC because of my nervousness that I cannot construct the invariant mass of the final state particles. But you can ask your question.
No, you want to comment on any other experiments?
Any other experiments for dark matter detection?
Yeah, because if you know the missing energy, you can probe it, the studies very easily. Right?
True, I mean, but we have the currently running machine is LHC where missing, see the missing energy and missing transverse momentum, they are similar. There is only one difference in the missing energy, the information of dark matter also goes, dark matter mass, I am sorry. In the construction of missing energy, because it is square root of S minus sum of the energies of the visible final state particles. So, the information of dark matter mass is tacitly embedded in the construction of missing energy, but which is not directly present in the construction of missing transverse momentum. So, therefore, if you want to extract, I mean if you do a simple exercise, you take the same dark matter operator with 3 different dark matter masses, plot their missing energy distribution. You will see that the peaks are slightly different. I mean, in context of ILC, as you can see here, the endpoints of this missing energy distribution, E gamma is missing energy essentially, because it's essentially square root of S minus E gamma. So, there is a information hidden of the dark matter mass in the end point of the spectrum. Okay? But if you plot the missing transverse momentum, they are overlapping. So, missing transverse momentum actually carries the signal of dark matter, but it is not conducive of differentiating between different dark matter masses coming into the production. If that answers your question. Yeah.
Following to that one, the missing energy from B decay, that is the belt to that take that first measurement, right? On this B2K nu bar. So anything to do with that? I mean, I don't know.
I mean, can you postulate about the presence of dark matter via that? I think Lipika, where is Lipika? Yeah, here she is. She is an expert on that. I think they are doing all kinds of this. Deepika, are you right? I mean, in saying that you can postulate the presence of dark matter. Microphone to her. I mean, I'm not an expert, but she is.
Since you cannot detect neutrino, so instead of nu bar, you can consider that it is a chi bar, like fermionic dark matter. So then, but your chi bar has to be less than mb minus mk. So you can take it as a dark matter. But
and then you have to construct appropriate models which will actually give rise to that interaction.
That fermionic
fermionic interaction, and I think there is a series of papers by Soumitroda and his collaborators where they were trying to construct these effective operators. He will talk about that in one of the guest lectures, and also postulate that this missing energy that you actually see in the flavor decays that can have a dark matter presence.
It has to be very light dark matter, right?
Yes.
Yeah, okay. I don't.
Because B is
Yeah, chi bar has to be less than 3 GeV.
Less than
3 GeV. I mean chi bar both.
B and K mass difference,
So-
right.
Can I ask?
Yeah, sure.
So in the beginning, you talked about realization. Now, what is the time scale of realization? Are we sure that the galaxies we are seeing are all realized?
Yeah, I don't know the answer to this question actually.
So
To
that
be
is
frank.
important, right? We are assuming realization. What is the time scale?
Yeah, that's I don't know. I mean, what is the time scale? I don't know. I mean, yeah, that's true. That what is the time scale of virialization? Yeah, I mean, you are taking a time average, but about what? Yeah.
And how do we make sure?
How do you make sure that that is there virialized? I don't know. I mean, in case you know, you can answer. Yeah, that's.
Sir, regarding the T channel, can we not have Higgs goes to dark matter and the propagator is the dark matter itself? Then
You mean that you can have something like this? You are producing dark matter for sure.
the
So you have okay. So you want to have this one.
we do
The
not
two
need
dark matter
additional
with one.
charge.
Yeah, because if you couple it to H dagger H, then it's a possibility. Yeah. So I'm sorry, I gave you a wrong answer, which was corrected by Ovik. You can have a T channel interaction just via H dagger H itself. I mean, because see, H dagger H, when you expand with in the unitary gauge that we talked about, like H plus V whole square, then you also have a term H dagger H, and then like so this will give you H plus V whole square phi square. So there will be a term phi square H, and you are saying that this is your phi, this propagator is also phi. Yeah, this is possible. Yeah. True. Okay, so I think we should end the session. Thank you, and we come back at 2:30, and then we have a guest lecture in the afternoon at 4, and most importantly, we have a dinner today, and you must come. And this place will be B-type community hall, and which is not very far from the guest house, a little far from Lohit, and very far from Disang. So, but yeah, okay. Huh? 7:30. 7:30 we assemble, and then we, yeah. Yeah? Yeah, I will try to make sure that he doesn't have to walk too far. Okay, see you in the afternoon.
Hello, 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 hello.
Okay. Okay. Right. All right, welcome back. So let me go recap a little bit what I was talking about. And so what I covered at the end of last lecture was looking at one term in the underlying Lagrangian, which is the one containing the pure vector fields, which looks like this, and analyzing it, pointing out that the fact that the fields, the light fields close into a light algebra, the light algebra implies that these type of structure constants vanish. And so, of the various coupling vertices that are allowed, that you may think exist, a few are absent. And in particular, the one that has two light fields and one heavy field. I remind you, the A denotes a light field, the X a heavy field. That is that vertex is absent. So let me then come down to this statement here, that operators such as this one are necessarily loop generated and argue how that happens. So for that, I'm going to use the board. Purple, not purple. Okay, so I have an operator that has 3 field strengths of the light fields. I know I've been calling them A, but since I'm going to talk about the standard model, I will use the notation I was using before and call the W's and call them W's. These are the W's. Inside it are the W plus, W minus, and part of the Z and part of the photon. So the operator in question has W mu nu. I'm just going to write it symbolically, cubed. The W in itself, the W mu nu, has 2 terms. One that has a derivative, and the other one that has 2 W's. The 2W term is precisely this one here. It's precisely this one here. And this is the derivative. This exact same form is followed by the field strength in the standard model. So when I do the cube part, I get terms that contain W to the n with n equal to 3, 4, 5, and 6. So the first thing I'm going to show is that by the way, if you have any process that at tree level can generate this operator, there ought to be some version of that process that generates the term with 3 guys and another at 4 guys, 5, all of them at tree level. Okay. And so I'm going to look at these 2 guys first. I'm sorry, not first, but only. Looking at number 3 first. So I'm looking for a graph that has 3 external legs and is a tree-level graph. And for that, I'm just going to list the possible graphs that do that. So the number of loops of any graph is equal to the number of internal lines minus number of vertices plus 1. But I'm telling you, I need this at tree level. So this is equal to 0. Next, my vertices in the Lagrangian have either 3 or 4 fields, because the underlying theory is a gauge theory. So 3 and 4 fields. And there is yet another topological relationship that says this: the sum of the vertices with n legs is equal to twice the internal lines plus the external lines. The external lines are 3 for this case. I'm looking at generating at tree level an object that has 3 external W legs, so 3 external legs. And I is equal to V minus 1. So I have 2V minus 2 plus 3. What is V? Well, V is this number, the total number of vertices. So V, oh, I'm sorry, this is NDM. I'm sorry, NDM. V is the total number of vertices, so this is equal to 2, the sum of Vn plus 1. So what do we get solving this amazing relationship? We get 2V4 plus V3 is equal to 1. V3 and V4 are numbers of vertices, so they're non-negative integers. So the only possibility for this, the only solution for this one is V3 equal to 1, V4 equal to 0. So the total number of vertices is 1. And by this expression, the number of internal lines is 0. So what I'm telling you is there's only one graph, one tree-level graph that can generate a 3-point vertex, and it's this graph with no internal lines whatsoever. Pardon me? Excuse me? This? Okay, so I expanded this, and there's a 3v3 plus 4v4. And then I put this thing on the left-hand side, and the 3v3 becomes 3 minus 2 is 1. This is the 1. And the 2b4 minus 4b4 minus 2, 4 minus 2 is 2. And you get equal to 1, this one.
No, I think she was asking
Oh.
about this replacing I by V minus.
Oh, this.
Yeah.
Oh, that's a topological relationship for the.
I plus E,
Yeah.
so I is equal to V minus 1.
Yes.
From number of units.
Yeah, this is something that you prove in general.
Yeah, exactly. Follows from the previous.
What's that?
This first line, that loop.
Oh, this follows from this first line. This first line follows by just analyzing how the delta functions work in a Feynman graph. Each vertex has its own delta function, and you eliminate all of them. There's one delta function left over for overall energy momentum conservation. Yeah, but it follows from this relationship. This is in any book in quantum field theory. In quantum field, I don't want to go through it because then I would have to start talking about Feynman graphs and expressing this thing in full detail. But this is a standard relation. Every book in quantum field theory has this expression. So it follows from once you substitute it. What I've done is I've substituted this v for I minus 1. I'm sorry, this I for v minus 1. All right. So this is the single graph that generates an object with 3 legs at tree level. At loop level, there's many of them. Okay? But our Lagrangian already has such a graph at tree level. It's the trivial contribution from the standard model. Among all the terms in here, there will be a series of terms where the little index A corresponds to the light generators. And those terms correspond then to the kinetic piece of the light gauge fields, which are precisely the terms in the standard model Lagrangian that we all know, and have nothing to do with the underlying physics in the sense that they don't involve lambda. So this is just the standard model. And this is not, the standard model and the vertex that can be is the one that comes from making a product, making a product of a derivative term and a quadratic term in an object such like this. The object that I'm looking at doesn't look like that. It's the cube of this guy has 3 derivatives, 3 gauge fields and 3 derivatives. The one that can be generated at tree level has 1 derivative and 3 gauge fields, missing 2 derivatives, if you wish. So the point of all this thing is that there is no way you can generate this object at tree level. It just doesn't happen. The structure of the theory does not allow it. And this is an example of what I call loop-generated operators. Independent of the nature of the underlying physics, this guy does not appear at tree level. So what does that imply phenomenologically? Yes?
If we relax the assumption that there is only one type of internal line.
Here.
So no, the first line. A is equal to I minus B.
No. There's no internal lines.
No, see, the first line, we have only I minus B plus 1, right? Yeah. We are assuming only one type of gauge boson, one type of internal lines up there.
So the question whether, if I'm assuming one kind of internal lines, the answer is no. Absolutely not. This is a completely general relationship for a graph that involves inside fermions, gauge bosons, or scalars. No assumption about this. This relationship is also true for all graphs. In fact, if you look in general allow for a full effective theory where you have vertices with 3, 4, 5, 6, and so on fields in them, 3 legs, this expression still holds. Where now it's 3, 4, 5, 6, 7, 8, blah, 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 kind of thing. Okay. But this is completely general. This comes out, again, of just counting when you put a graph, each vertex has to obey energy momentum conservation between each of the vertices. So these are the number of free integrations that you get after you impose energy momentum conservation at every single vertex. So the one triple gauge boson vertex that you can get at tree level is one that has 3 gauge bosons and 1 derivative. The one that comes from this operator has 3 gauge bosons and 3 derivatives. This guy, therefore, cannot be generated at tree level, must be loop generated, independent of the physics underlying the standard model. And this is one example of such iteration. So, for example, so what does that mean? It means that this guy, the operator that is this O, the coefficient for this operator, will have a 1 over 16 pi squared from the loops that has to generate it times the 1 over lambda squared. So this represents an additional suppression for this operator. There are operators that do not suffer necessarily from this suppression, but this guy does. You will often see people talking about measuring triple gauge boson vertices. Those are these operators. They're talking about measuring this coefficient precisely. And when you get, and for example, I think one example in the particle data book, it says that this is of the order of 0.1 TeV squared inverse. Okay, this is actual. They measured, I think it's the W photon coupling. And they put a limit on the difference between the W photon coupling produced by the standard model and use that deviations from that coupling, and they use that to put a constraint on this CL. Okay, this does not mean that the lambda is of order 3 TeV, which is what this would mean. But you're off by an order of magnitude. So instead of 3 TeV, you have a limitation of 300 GeV. And what you're saying is that there's no new physics at 300 GeV, which is true, but not new. We knew that for a long time, 10 years, long time. So it's powerful that the experimentalists can do this measurement. It's fantastic, but the physical implications from them are not particularly exciting because they chose an operator that is necessarily loop suppressed. And that is why this provides, I think, an example of why calculating or finding out which operators are loop generated and which ones may not has some use. Okay. So experimentalists go and they measure. The challenge is to extract CL or bound, put a bound on CL. That's their job. It might be very difficult, and that's why they do it. Our challenge is to take data and say what it has to say about nature. And for that, we need to understand how to translate a measurement to a physical parameter. And it's in that context that these statements that I'm telling you, that these calculations and these arguments are useful. Any questions about this? This is the main, yes sir. Use the microphone. Okay.
Hello.
Yeah.
So here I equal to 0 implies that this W cube is loop generated.
No, yeah.
Yes, because there can't exist any internal line which implies any W, right?
Exactly.
So that's why we can't go, let's say W4, that we can take. Only up to W to the power 3 we can take. That's why it is the case.
So, no, but I can also say the same thing about 4 guys. I can do 4. I was going to do 4 right now. So bear with me for 4. Okay? Can do the same thing for 4.
Actually, I don't understand that how I equal to 0.
Means
it implies...
Means it's a graph without internal lines. It's a dot. No internal lines.
Yeah.
So, it's this.
Yes.
This graph is this.
Yeah, yeah.
Okay, so what part of the Lagrangian has, this is just a term in the Lagrangian, so what term in the Lagrangian has 3 vector bosons? And I tell you, it's this times this. There's nothing else.
Yeah.
And this times this is derivative vector, vector, vector. The one I'm looking at is derivative, 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 vector, vector, vector. I'm missing 2 derivatives. So, the only vertex that can, the only thing that Lagrangian can provide is this times this, the one I'm at tree level. The one I'm looking for is not it. Therefore, this is Aristotelian logic, the only leftover possibility is that the cube of this guy must be generated at loop level. Because if it were at tree level, I get a contradiction. It doesn't happen. Okay? At 4, and I want to do this also at 4 because it uses this. Okay? At 4, there is one graph that can generate an object with 4 external lines. Okay? I'm going to erase this because I'm not going to use this. So for n equal to 3, that's the way it goes. For n equal to 4, the graph is this. Now, in between here by Lorentz invariance, it has to be a boson. So it has to be a scalar or a vector boson. Scalar or vector boson. This is a light guy, so I'm going to A, light guy, light guy, light guy. So this can be a heavy guy, and I'm going to exclude the case where this guy is a heavy one. So let me look at this possibility. Well, this possibility has an internal line, great things. This has a propagator that goes like 1 over p squared plus minus a heavy mass, lambda squared. So when lambda is or momentum is small compared to lambda, I get my 1 over lambda squared. I'm getting encouraged. Okay, this is actually working out for me until you realize what this vertex here, where does this vertex come from? Again, it comes from this guy. It's a 3-body, a 3-field vertex. It comes from only from the Lagrangian. That's where the only origin. And what do I have? Well, this is my Lagrangian, and so it has to come from a product of a term like this with a term like this. That is the only vertex in the Lagrangian that has 3-gauge bosons, and therefore it is proportional to the structure constant involving 2 light fields and a heavy guy, which is 0. So the graph is 0 because of this. And you might object and say, wait a minute, but you told me you can generate it also with a scalar in between. That is true. That is true. I'll come back to that later. But this illustrates how at least this condition prevents the heavy gauge bosons from generating my friend here. Or I'm sorry, a section of this friend here, the one that has 4 gauge bosons in it. Other questions? The rest of the calculation, or the rest of the argument, is based again and again on properties of the group, properties of spontaneous symmetry breaking, things like that. So I'm going to mention them, but it will be exhausting for me and much more for you, for me to actually go through all the calculations in detail. And unfortunately, I can tell you things, but you have to think them through. So it's impossible for me to force you to think them through. So I'm just going to mention how things go and think them through. If you have questions, then I'm here until Friday, okay? And the reason I'm asking you to, or suggesting to you that this is a worthy exercise to go through this thinking process is precisely this argument here. You want, it's okay. The interpretation of the experimental results require us to understand the nature of the operators at hand. And this is the process of doing that. All right. Next up, fermions. So the fermions, the term in the Lagrangian that connects fermions and vectors are just the kinetic pieces. It involves the covariant derivative. And this is for the whole theory, the underlying theory, which I remind you, I've assumed is a generic gauge theory. In it, I have fermion fields that I call collectively chi. And there's little psi, which are light, and big psi, which are heavy. And again, I have my vectors v, and the vectors v also have light and heavy, A and X. Right? And then I have a property of group theory in spontaneously broken gauge theories. That is, the generators of the algebra, of the group, sorry, the group generators are associated with either light guys or heavy guys. And the ones for the light guys I will call the unbroken generators. And these just do not mix representations with different mass. Just don't. And therefore, there will be no vertex that has one light, one heavy, and one light guy. I must have a light vector boson because this is a property only of the generators associated with light gauge bosons. And then this type of object is excluded. You can still have operators with 2 lights and 2 heavies, and you can have a mixed guy with a heavy guy, but you cannot have light, heavy, light. If you remember, in the previous, we cannot have a light, heavy, light. We couldn't have 3 gauge bosons, 2 light, 1 heavy. Here, we cannot have a triple vertex involving fermions, 2 light and 1 2 light and 1 heavy of this kind. Okay, but we can have this type, which is light, light, heavy. Okay, but just like that. So another way of saying it, so far, the A guys connect either to 2 heavy or to 2 light, but not to a heavy light. I encourage you to think this through. And a little bit more complicated, are the scalar part. The scalar guys I denote by this by theta. The full gamut of scalars I call theta that are separated into little phi, which are light, and big phi are heavy. You see a pattern here. Capital Greek letters for me in this calculation are heavy. Small case Greek letters are light concerning the matter fields. For the gauge fields, it's A and X. Yes? You have a counterexample. Tell me later. Don't a heavy vector-like fermion. Okay, all right. I need to write it down. I need to make time to try to think how to answer this. Yes, well, okay. So you have a heavy vector-like quark. Is it a doublet? No, you have to tell me. It's your model. It's a doublet? Okay, it's a singlet. And then it's a right-handed singlet? No, vector-like. Vector-like. Singlet. Singlet. And?
It goes to, it has a vertex, let's say, because I know the decay, like, it goes to light quark and a standard model.
Okay, so what you want is this Q guy goes into a light quark and a standard model case.
Or standard model gauge goes on, let's say Z.
Or a Z.
Yeah.
Okay. How does this happen in your model?
Not my model, I'm just saying.
It's your model, you're telling me.
All these top partners charge, let's say, has this.
Okay, so let's see how it can possibly be. Let's see how it can possibly be. It's supposed to happen at tree level.
Yeah.
Tree level. Okay, tree level graph. And so you have one. We just argued that the tree level graph, a process with three external guys, looks like this. Q, Q, Z. How do you generate this? Oh, he told me it's a singlet.
Let's say you have a standard model quark doublet and a Higgs and a right-handed and this vector-like quark.
Okay.
It's the same charge as the right-handed quark.
Okay. So I have.
Let's say I can go and write down the term. Standard model left-handed quark doublet.
Standard model left-handed quark doublet.
With the Higgs.
With the Higgs.
Okay. And in the Wudka introduction, what you write? You replace this with the right-handed quark, right?
Sure.
So let's say this capital Q has the charge of a right-handed quark.
Okay.
So then this is a perfectly allowed term.
Okay.
And then you diagonalize.
And you have a term that goes like this. MQ Q bar Q.
Yeah.
And the hypercharges somehow arrange themselves. Okay. And this is the Lagrangian. Okay. And what else?
When Higgs get the waves, it mixes these two things, the quark.
Okay, but
You diagonalize it and you go to mass basis, but somehow this.
okay, the Z comes from where?
Sorry?
The Z.
Oh, there is a coupling of, let's say, if this Q kind has preferably E1Y hypercharge, the small Q can have E1Y hypercharge.
ID slash.
Yeah, and from there, when you diagonalize the mass basis, they have a coupling, the Z off diagonal coupling.
Okay. All right. And what you want is from here to get what?
You have also Q, small Q bar D slash small Q term. The usual kinetic term for standard model quark.
Okay. More. And you want this also? right? Yukawa and so on. Okay.
It will be different. It will not be with the same cube. It will be left and right. Yeah.
What is left and right?
Yukawa will not be with the doublet. Both of them will not be with the head.
Count the right. You're right. So there's no mass. You're right. Sorry. Sorry. There's no mass? Okay. Cube.
So you write down the mass matrix for this quarks, right? What is 2 by 2 mass matrix, diagonalize it.
Yeah.
Generate this vertex, right?
Or to go-
Standard searches are going on.
No, I understand what you're saying. So what Sanjay is saying is from here, one can get the mass matrix for this. When this gets a web, you have something like this. Mass matrix, QQ is M. Let me just call it big M, okay? So I have fewer labels. I have a
Yeah, so one of these off diagonal
Vev.
one will be non-zero.
I have a Vev, I have a 0 here.
No, I think that will be Yukawa. Another diagonal will be there.
So it's light. 0. Okay, well, okay, so it's a Yukawa.
And one of the off diagonal entry will be 0, the other will be non-zero.
Not exact. Okay.
Yeah, it will be a 1 or 2 will be 0.
All right. I'll have to work through the model itself because this is not quite the end of the story, right? You have the right-handed guys and so on. But so this is for you a counterexample to this statement, right? To this guy. Because there's mixing.
Oh, no, there is a statement, sir. That's what the unbroken generator, TL will not. But this statement will be when the Higgs vector.
I'm saying, I was going to say, I was about to say, you're relying,
On the
okay,
generator. Yeah.
so where he screwed up,
Fine, but I got the point.
where he screwed up, no, I'm sorry. No, what I meant, why are we arguing? Because the whole point is that the mixing that he's relying upon requires the Higgs to get the vacuum expectation value. When that happens, the light generators get broken. In the standard model, there's three broken generators. We get 3 heavy guys, 1 massless photon. I am looking at the theory when the spontaneous symmetry breaking, if any, occurs only at the high energy limit and not yet at the level of the light theory. So another way of saying it is if you allow for the breaking of the standard model, this is true up to small factors. In my world, small factor is 250 GeV. That's small. That's light. Okay, so that's small.
Is there any possibility for radiative correction?
For a
Is there any possible contribution of radiative correction with the drill?
Oh yes, everything is at tree level. If you have radiative corrections, this happens. Radiative corrections generates this thing, generate this guy, will generate everything. But the point of this is that all radiative corrections come with this suppression factor. It's just a numerical factor that's useful phenomenologically, the 1/16 pi squared. Okay, that's the whole thing. But yes, you're absolutely right. The radiative corrections, they generate anything. In fact, they generate everything. And so, yeah, absolutely. Okay. So the low energy theory, yeah, but thank you. That illustrates something I should have super emphasized and I didn't, which is the low energy symmetry is not broken. Not broken. You can say how that can be is that in my world, I'm at the temperature of 257 degrees, 250 GeV, degrees Kelvin, equivalent, and so the standard model is not broken. But the lambda is much larger than 256 GeV by assumption, and so even at my hot temperature of I don't know how many 10 to the x degrees Kelvin, the underlying symmetry, if broken, is still broken. I mean, it's not okay. All right. Thank you. Thank you, Sanjay. That's very useful. Okay. Then let me look at the scalar vector interactions. This comes from this guy, and I'm going back in time. Okay, so when and if a heavy guy gets a VEV, it generates terms that have two vector bosons and a scalar. Because, you know, this is the usual thing of spontaneously broken gauge theories. I want to examine this vertex. And so it looks like this. I've actually expanded it. This is the VEV. It comes from one of these guys. And here are two generators. This comes from the covariant derivative. And there's the vectors associated with it. And then I have another scalar field here. Now, as in the other case, the unbroken generators do not mix heavy and light. And because they are unbroken, they annihilate the vacuum expectation value of this guy, because they're unbroken. That's the definition of unbroken. And so, if this is a light guy, you will get 0, and the corresponding cubic vertex of it will vanish. Okay, so that's the type of argument. I'm not going to go through what it implies in all possible situations, but in this case, that's what it implies. Okay. Another observation. These are the broken generators, the heavy guys. This object here points along a Goldstone direction. And therefore, it is orthogonal to the physical directions, be it heavy or light. And finally, gauge transformations do not mix the physical guys with the Goldstone directions. And all that says this: that if you have a heavy generator and any other generator acting on a light guy and a heavy VEV on the left, you get 0. This shows up here. So I use those two things, this and this, to again exclude a bunch of vertices. In fact, 11 out of 31. These are the ones that are allowed. For the scalar and vectors, these are for the fermions and vectors, and these are the forbidden ones. This vertex of 3 light guys is forbidden because the standard model of the phi is a doublet, so you cannot make a singlet out of 3 doublets. The other ones involve some of the heavy fields, and so they do require the arguments I have been using. So these two conditions, that this is true, and this is true here at the bottom, and this is true here at the bottom, imply that a light, heavy, heavy, and so on vertices are 0. This vertex doesn't occur because I have not broken the standard model symmetry. That is another. When you break the standard model symmetry, you will generate a Higgs ZZ vertex, right? But since I have not broken it, this just doesn't show up. And the quartic vertices forbidden are these guys for those involving bosons only. So what do I do with this? I found the vertices that are allowed and the vertices that are not allowed. And with it, I can construct painstakingly all possible graphs that have propagators that are heavy, here denoted by a heavy line, and they may be either bosonic, indicated by a dotted line, and that implies also gauge bosons, not only scalars, or fermionic, indicated by a continuous line with an arrow here. All the external guys are light. The heavy dots denote super renormalizable vertices of coefficients of order lambda, which I told you already they are problematic, very problematic, but I'm listing them anyway to be as complete as possible. These are all the possible graphs and the kind of thing. If you don't put in coefficients of order lambda here and here, this graph is not of order 1 over lambda squared, but in fact is of order 1 over lambda to the 4th. It's easy to check. And so that's why it necessitates this thing. Any graph that you might cook up that is not in this list is not in this list because it involves one of these vertices in one way or another. So this is, this project, when I went through it, had 3 painful stages. And painful stage number 1 was doing this. Painful stage number 2 was doing this, finding which graphs are allowed. And the last painful stage was to look at these graphs that I generate, that embody, by the way, all possible terms, all possible graphs at tree level that can generate, that have a coefficient of 1 over lambda squared. Okay, so these are the graphs that correspond to my dimension 6 operators. And the last painful stage was to match these graphs to the list of operators that I showed you a few lectures ago for the standard model. Some of the operators will correspond to nothing here. So for example, you see no graph that has 3 dotted external lines. These are the ones that I've excluded earlier today. Those are the ones that are forbidden at tree level. There are graphs, there are operators that certainly show up with this guy. Paramount among these is a 4 Fermi interaction. 4 Fermi interaction. It has 4 fermions outside and a boson in the middle. Kind of thing. That can be generated at tree level by some boson in the middle. Okay? In contrast, operators with 3 bosons outside cannot be generated by anything. In a tree level. There's nothing you can do. You might say, what happens if my theory doesn't have that boson? Well, in that case, this operator that could be generated at tree level, in your theory, isn't. It's generated, if at all, by some other means using gradative corrections, because you don't have the right intermediary to do this. Okay? So that's why I call them potentially tree-level generators. If you have the right type of heavy physics, you generate them. If you don't, well, you may still generate them, but not at tree level. On the other hand, the loop-generated guys are always generated loop, no matter what kind of new physics you choose. All right, so here's the list, half of the list of operators that I showed you earlier, and I've highlighted those that are potentially tree-generated. All the other guys that you see here, triple vector bosons, 2 vector bosons, 2 scalars. These that look like, these have 2 fermions and a W and a scalar and have like a magnetic coupling. All these guys have very cool experimental signatures and would be observable if the coefficient weren't suppressed by this 1 over 16 pi squared. But reality being what it is, the 1 over 16 pi squared is there, and though the effects look cool, they're tiny, too small to be seen. So let me describe briefly what these guys are. Yeah, these represent changes in the self-interaction of the Higgs. This guy is interesting. It is the oblique t parameter. The coefficient of this guy represents deviations from the standard model of the oblique t parameter. This guy are Yukawa-like. This part is precisely the standard model Yukawa. It's multiplied by 2 scalar fields. This guy, as I mentioned briefly some time ago, generate in corrections to the interaction between the gauge bosons and the fermions, like the Z and the W. In fact, all these are the corrections to the Z coupling to the fermions, leptons, left-handed leptons, right-handed leptons, and quarks. And this one at the bottom that's covered by this thing, I apologize, is a correction to the coupling of the W to the up and down quark. There is no correction to the W coupling to the electron and the neutrino. There's no counterpart of this guy. It's forbidden by gauge invariance. And then all the 4 Fermi interactions, all of them can be generated at 3 level. Now, you may say, well, how do you know? And the answer is, I can't know a priori. I can know a priori that all these guys have small effects. Whether these guys have small effects or not, small, I mean suppressed by this loop factor, depends on the underlying new physics. For some kinds of new physics, this happens no problem at 3 level. Other kinds of new physics, it happens only in loops. In fact, let me point out something. How can you ensure? How could I ensure? Let me illustrate this. These are what I'm telling you is that these are all the possible graphs that give you terms of 1 over lambda squared when you integrate out the heavy guys. These are all the, and they have one thing in common. All the graphs have at least one vertex that involves 2 light particles and 1 heavy guy. 2 light particles, 1 heavy guy. 2 light particles, 1 heavy guy. 2 light, 1 heavy, and so on. All of them are. Okay? So imagine a type of new physics where that has a discrete symmetry. All the light guys, the standard model is even under that symmetry. All the heavy guys are odd under that symmetry. Okay? And assume that that symmetry is not broken. That means that terms that have 2 lights and 1 heavy are forbidden. All these vertices that I mentioned are forbidden. All these graphs are forbidden. And therefore, none of the operators can be generated at 3 level by this type of new physics. And you know or have heard of an example of this, supersymmetry. The parity thing is R parity. R parity. R parity forbids then the heavy guys in this version of supersymmetry are all the super partners to the fermions and the gauge boson. All the super partners, in fact, and all the super partners. And so those are odd under R parity. All the normal guys are even under R parity. And therefore, if you imagine that all the super partners are heavy, then their effects at low energy are always suppressed by 1 over 16 pi squared. That is a very good reason why supersymmetry has been so successfully surviving over all these years, because the corrections it produces are small. Many of the corrections that you look at supersymmetry is because the theory requires 2 scalar doublets. And so there's a lot of an almost infinite number of papers that talk about the 2 Higgs doublet model. And it's partly motivated by supersymmetry. But I'm not talking about a case where the 2 Higgs doublet models are the heavy physics. I'm talking a case where all the supersymmetric particles are the heavy guys. The low energy theory, in this case, has an extra doublet. Fine. You know, that's the way it goes. But the heavy particles, the one that guarantee you have supersymmetry, all their effects are suppressed by 1 over 16 pi squared. Not only by their mass, by their heavy mass, but by this loop factor. And therefore, they are very well hidden. There are other examples of this thing. but I will not go into them. I think it's a good thing to keep in mind that one can find easily by this simple argument of a parity symmetry, models of new physics that that generate all operators, all these operators at loop level. So, purple potential tree level generated, not purple loop generated. So which one of these? Again, let me reemphasize. You have self-Higgs interactions, you have the T parameter, you have your Kawa-like couplings, you have the WZ couplings, and you have 4 fermion interactions. Those are your windows into new physics. In most cases. I will come, when I go at the applications, one case that I know of, very clear, where loop-generated operators actually are of interest, and we can probe them. But that's a very specific case. Okay. Any questions? Okay, let me finish by doing just a few observations. I've constructed for you almost to the end that the number of PTG operators is 1 in dimension 5. I constructed it. It was this Weinberg operator, and you probably know it. If not, I really encourage you to go and check it out. That the operator can be generated at tree level by precisely 3 types of new physics. It's a very elegant and interesting fact. In dimension 6, I did not count them for you, but the purple guys here are 39 of them for 1 generation. In dimension 7, there are 20 of them. I'm not listing them at the moment. And again, let me re-emphasize that presumably the largest NP effects that we can observe come from the PTG operators. Okay. There are, and again, this last statement, there are 1 blue process in the standard model that are very interesting and are readily measured, and such as the decay of the Higgs into 2 gluons. That's how the Higgs is produced at the LHC. Since we measure the Higgs, we measure this. Okay? And for these rather rare type of type of processes, the loop generated operators will also be important. But this is a rare instance. Okay. And with that, let me stop. Any questions? Okay, so the takeaways from today. There's a long formal set of calculations. First, the hierarchy defined by the effective theory is consistent with renormalization. Whether you want to do renormalization or not, which I recommend you do not, but it's a free country, it's different. You can be reassured that the model, the theory is internally consistent in that sense. Second thing, one can segregate operators into those that are generated at tree level and at loop level. The ones that are generated at loop level have that property always. The ones that are identified as potentially tree generated may or may not have that property. And I've argued for the phenomenological benefit of doing that classification and obtaining it. This is actually useful in that respect. You can do this not only for dimension 6. It's more painful to do it for dimension 8 and dimension 9 and so on. Shubha and I did it for dimension 7, and that was not fun. So I don't recommend dimension 8, but again, it's a free country to do it. Just keep in mind that there are very, very few processes that are sensitive to dimension 8 and 9 operators. And so, again, just whether there's payoff at the end of such a big effort. Okay. What I'll cover tomorrow is applications. I will cover applications such as neutrinoless double beta decay. Well, there's no secret. I will talk about Higgs physics, simplified. I'll talk about neutrino physics a little bit, and talk about lepton number violation in the guise of the neutrinoless double beta decay. But that is tomorrow. That is tomorrow. Today, I'm done. I'm sorry, I'm done with this. But any questions? I'm babbling on in the hope that some of you will be brave enough to ask a question that might be nagging you. And okay, all right. T, thank you.
Hello. Audible?
Okay, so good evening to all of you and welcome you all to the fourth day special guest lecture. And today we are very happy to have Shankho from IMSC Chennai, and he is going to have a very interesting discussion, it seems from the title, Collider Physics plus plus in Effective Field Theories, and then a highly with a question mark biased perspective. So with this, Shankho would like to start.
So before starting, I would like to thank Shubhoda for inviting me, and so I was last here during WEP in 2019, so it's always good to be back here. So the topic is very broad and very biased because I work on these areas. So we can get started. So because the topic is on collider physics, I'm going to talk a bit about colliders. So there have been colliders in the past which have discovered a lot of particles for us. So for example, there have been E plus E minus colliders like the SPHERE within the SLAC facility, which discovered the JSI meson along with BNL. Then Petra, which in DAISY, which discovered the gluon jets. LEP collider, which was at CERN, measured very precisely the mass of the weak bosons, the W and the Z bosons. So here you can see the LEP facility. On top of that, I'm not sure how clear the numbers are from back at the back. So LEP was able to constrain the Higgs boson mass even before its discovery. So LEP said that the mass of the Higgs boson should be more than 114.4 GeV. Then there were past proton-proton as well as proton-antiproton colliders. So ISR was the first PP collider. Then the SPS, which used to be an injector of the E plus E minus beams into the LEP collider and now acts as an injector to the LHC. So it used to be a collider on its own, and it discovered the W and the Z bosons. Tevatron was a PP bar collider in the US, and the top quark was discovered here. And apart from LEP, Tevatron was also able to put strong constraints on the Higgs boson. For instance, it said that the Higgs mass cannot be between 100 and 103 GeV and some 147 and 180 GeV. And in the BB bar final state, it was able to like not discover, but it saw an evidence of the Higgs boson between a mass of 115 and 140 GeV. So Tevatron was a very, very important machine, and recently you probably have heard about the W mass measurement controversy from recent analysis of Tevatron results. So on top of that, there was the fixed target facility at SLAC, which discovered the charm quark, the quark structure inside the protons and the neutrons, and it also discovered the tau lepton. So this is the LEP facility. It used to be at CERN. It used to be a 27-kilometer radius tunnel across, sprawling across Switzerland and France. And this same tunnel was taken over for the LHC. So LHC has many experiments, but there are 4 major experiments, the 2 general purpose detectors, ATLAS and CMS. Many of you have heard of these, and then LHCb and ALICE, but there are also many small experiments which I'm not going to talk about today. So LHC has been running since 2009 and discovered the Higgs boson in 2012, and since then they have been trying to precisely measure the properties of various standard model particles, as well as trying to find new physics directly. There is a present heavy ion collider, which is the RHIC. It has been running from 2000, and it studies quark-gluon plasma and physics of the early universe. So the second edition of it is going to be the electron-ion collider, which is going to be something very interesting. So now present E plus E minus collider in Japan, Super KEKB. So it has been running since 2018, and it made precise measurements, is still making precise measurements of B mesons. So future colliders. So again, this is a very, very interesting as well as like we are not sure what's going to happen. So there are many countries competing to build new future colliders. So for Japan, for instance, has been planning to build the International Linear Collider. So which the feasibility studies show that it would be very important for Higgs boson precision studies, electroweak interactions, and more. In China, the Circular Electron-Positron Collider is going to be a Higgs factory. If it happens, it's going to run at 240 GeV center of mass energy. Precision studies of the W and the Z boson. And then the future circular colliders at CERN, which is supposedly going to be a 100-kilometer tunnel if it is built at all. So right now, feasibility studies are going on, but those are not enough. So people need to convince the various governments that these need to happen and need to present interesting cases why these need to be built. So I am hopeful that many of you in the audience will probably be able to show cases why we need future colliders in the like any of these future colliders. So FCCEE is going to be a precision Higgs machine like the ILC, and it will also be able to measure very precisely, like to a per mil level of precision, the properties of the W and the Z boson. So there are future hadron collider prospects. So this same tunnel will be replaced by proton beams in the very distant future. So it will be useful for direct searches for new particles which might be very heavy, which are not accessible at the Large Hadron Collider. It will help us study the Higgs potential very, very precisely. For instance, we know that the Higgs self-coupling is extremely tiny, so we can only measure the Higgs self-coupling through either di-Higgs production or tri-Higgs production. So di-Higgs production will be probed to a certain extent at the end of the run of the Large Hadron Collider, but tri-Higgs, it's extremely difficult because the rate is too small. So it's also like supposed to study the physics of the early universe. And then another future collider proposal is future muon colliders. So direct search for new particles with very clean collision environment, much cleaner than hadron colliders. So now I'm going to like slowly delve into effective field theories here. So why we need effective field theories, why effective field theories suddenly became so interesting at colliders. So I'm going to talk about model theistic versus model agnostic. So I'll tell you why this is model agnostic, so not exactly model independent effective field theory approaches. So I took this cartoon from Tim Tate. So here you see that like just for dark matter, there are a plethora of theories. There are so many different kinds of theories which can give rise to dark matter candidates. And this is not the complete picture. There could be many more. So why do we not want to study this any longer, or rather keep it as an aside and start talking about something somewhat more model independent? So no direct hints towards new physics which explains the various observations like dark matter, existence of dark matter, massive neutrinos, more matter over antimatter, and so on, or physics beyond the standard model. So there are many models available to us, but there is no consensus like which model is the correct one. The reason is that every single model that we study comes with an additional baggage of many other particles, many other interactions to study. So until and unless we get to know all of this additional baggage, it's very hard to say like what kind of new physics we are looking at. So the questions that we ask is that like, is the new physics that we are seeking, is it hiding somewhere? Like just we are obviously missing for various reasons, like we are not studying the proper channels, maybe we have not yet taken enough data, or is it just above the present experimental reach? Is it just above a few TeVs that the LHC is not being able to probe at the moment? So, or are the interactions with the standard model particles extremely feeble? So if that's the case, so we may never be able to discover these particles, or we may need a lot more data. So we don't know the exact reasons why the new physics has not been discovered yet. Another very crucial thing is that the theoretical and the experimental precisions may not be good enough at the moment. So it's possible that the experiments will reach even better precision, and that even from the theory side, we match that level of precision through, for example, higher order perturbative QCD calculations, higher order electroweak calculations, and so on. So imprints of new physics could show up as tiny deviations rather than like something very to the face. It could be some tiny deviations in standard measurements. So these could be hints. So that's why it's very, very important to minimize theoretical uncertainties. So this whole school has been about effective field theory, more precisely standard model effective field theory. So I'm not going to go into a lot of it. So but you have all seen that like in standard model effective field theory, where the EFT is written as a linear realization, we have the standard model dimension 4 Lagrangian, and then we have operators in increasing orders of the mass dimensions. So Joydipta has discussed this in great detail. So there are many approaches to effective field theory like standard model effective field theory. So one is the bottom up approach, where we do not know what kind of new physics we are looking for. So we are ignorant and we write down all possible gauge invariant operators, gauge invariant under the standard model gauge group. And otherwise, if we say that we know what kind of new physics we are looking at, then we take our favorite physics beyond the standard model scenario, we integrate out the heavy fields, and then we get a subset of these operators that we would have obtained had we taken the bottom up approach. There's something called RGE equations. So for example, the operators that we get are at a cutoff scale of new physics. However, if we want to see, we want to study the picture at some lower scale, we would need to run down these operators, and we will see some interesting things, like for instance, some of these operators would mix with each other. There might be new operators which would be created, and so on. So for example, LHC has not yet found conclusive evidence of any BSM physics. So there are usually two broad methods to study. So for example, model dependent, as I was saying, that take a model, preferably a UV complete model, and study all of its signatures very carefully. Otherwise, take a somewhat model independent approach and parameterize our ignorance as low energy effective field theory formalism. So the standard model, or any BSM theory for that matter, becomes a low energy effective field theory valid below a cutoff scale lambda. So this leads us to choose a set of low energy degrees of freedom specifying the UV cutoff scale and the symmetries. So this is a cartoon taken from Francesco Riva, and here you see that the bigger theory which might be there is assumed to supersede the low energy model above this cutoff scale lambda, and the EFT effects can manifest themselves as deformations in various angular variables. So some kind of delta r, or like some azimuthal angle separation between some leptons, or some excession events in high energy tails. So because I said these will be in all probability very tiny deviations, we need extreme precision in theoretical understanding. So what is the standard model effective field theory? So it's an EFT which is constructed about the electroweak preserving vacuum out of the Higgs doublet phi. So Higgs doublet is the key phrase here, which linearly realizes the electroweak symmetry breaking. So the SMEFT can be written as a Taylor expansion about phi equals 0 in terms of operators in increasing mass dimensions, as I said, and the operators invariant under standard model gauge symmetry, which is SU3C cross SU2L cross SU1Y cross U1Y, and these are suppressed by powers of new physics scale lambda. So lambda for dimension 5, lambda squared for dimension 6, and so on. So for standard model effective field theory, when we expand operators, we see correlations between various deformations. So for example, let's take this simple operator H dagger sigma AH, W mu nu A, B mu nu. So this is the non-abelian W mu nu. And once we expand this, we see that we get interactions of the form Higgs with photons, effective vertex, Higgs with a photon and a Z, Higgs with two Zs, Higgs with two Ws, along with triple gauge couplings like two Ws and a photon, or two Ws and a Z, as well as the S parameter, which is the W mu nu, B mu nu. So from one single operator, we are getting so many different kinds of deformations. So if we take various operators, we get different kinds of deformations which we are able to correlate. So as an example, at the LEP collider, we were able to constrain the triple gauge couplings very, very precisely. So, through the Z pole observables, so Z decays and so on. So, the thing is that even though the Higgs was not discovered back then, if the SMEFT structure is true, back during the LEP days we already had information about the Higgs even before discovering the Higgs. So, that is a very interesting thing that like this SMEFT framework encapsulates. Before going on to the various discussions about SMEFT, something I just wanted to highlight which has not been discussed, probably Shubhoda asked me to just highlight this, is the Higgs effective field theory, or the HEFT. So, HEFT is the most general parameterization of low energy physics with only the standard model degrees of freedom. So, in this cartoon, in this way we can show that like the HEFT will form a superset of SMEFT, which will form a superset of the standard model. So, is there any scenario where only the HEFT can describe low energy effects of the BSM? So, there are instances, and I have kept some in my backup slides. So, later on I would encourage you to go and look up scenarios where SMEFT is not going to be enough. So, low energy interactions only follow the U1 electromagnetic. The interactions cannot tell us more about the properties of the microscopic theory. So, new non-decoupling strong dynamics leads to spontaneous electroweak symmetry breaking, which leads to a Higgs-like scalar. So, in SMEFT, what I told you before is that all these heavy physics, they are decoupled from the standard model, like they are at very high energy scales. But in the HEFT scenario, that might not be the case. So, some of the particles may get some of their masses or part of their masses from the standard model, like electroweak symmetry breaking. So, the standard model in the HEFT scenario is not recovered when all the BSM masses are taken to infinity. So, in SMEFT, like if there is any non-analyticity in the Lagrangian, they could be waved away by field redefinitions, but in HEFT they often may not be. So, this arises when new states are integrated out, they acquire masses from the electroweak symmetry breaking. So, this violates decoupling. So, unlike in the standard model EFT, where the premise was that the Higgs is a part of a doublet, here the Higgs is considered a gauge singlet of the SU2L, and the Goldstone bosons are an SU2L triplet. So, and these are treated separately, unlike in the standard model effective field theory. So, the Goldstone bosons are actually embedded in this unitary matrix U, and the Lagrangian for the HEFT can be written down in terms of these. So, it's a subset of the Lagrangian. So, there's a Higgs term which is linked with the d mu u dagger d mu u. So, Shotoda actually discussed this trace yesterday. So, I encourage you to go back and see this, how to actually calculate this trace. And then we have the kinetic term for the Higgs, we have the Higgs potential, and then we have the Yukawa terms. So, see here that unlike the SMEFT, all of these terms, this A, B, D, all of these parameters are independent of each other, they are not correlated. However, in SMEFT, at every dimension these couplings are correlated, but in HEFT they are not. So, these are the differences between SMEFT and HEFT. So, SMEFT, for instance, is the most general set of local, it encapsulates the most general set of local operators which are invariant under the standard model gauge group. For the HEFT, its manifest gauge symmetry is SU3C cross U1 electromagnetic. In SMEFT, the operators are suppressed by powers of the new physics scale lambda, whereas in HEFT they are suppressed by the electroweak breaking scale V. In SMEFT, the low energy states are modeled using fields transforming linearly, whereas in HEFT these fields are transforming non-linearly using a multiplet of the Goldstone bosons. So, the observed Higgs in SMEFT is a component of an electroweak doublet, whereas there is no relation between the Higgs and the Goldstone bosons in the HEFT scenario. So, SMEFT has a more restrictive symmetry structure, as I discussed. There are less number of parameters which are correlated. The HEFT has a less restrictive symmetry structure. There are many more number of uncorrelated parameters. So, now I am not going to discuss HEFT anymore. So, if you have any questions, you can ask me in the end. So the types of particle discoveries or particle physics discovery. So this is the one that's been tested very well. So discovery through resonance, this is the tested paradigm through which we have discovered all the particles that we know of today, the resonance. However, as I said, that it's possible that we may not be able to find new physics at the LHC, because it has been 12 plus years since the Higgs discovery in 2012, and we have not seen any direct evidence of new physics, especially in the high energies. So this new paradigm, as I said, is discovery through precision. So it could be discovery through some difference in angular observables or some excess of events in tails of certain distributions. So we would require percent or smaller level of precision in order to be sure that we are discovering something. So there are various types of uncertainties in particle physics. So I'm going to discuss a few here. So there are experimental systematic uncertainties, which include instrumental uncertainties, uncertainties due to calibration of energies, scales and resolution of detectors, and more. Then there could be experimental statistical uncertainties, which stem from finite number of events recorded. So the more number of events that we record, the less the statistical uncertainties become, and the systematic uncertainties are also being improved gradually by the LHC. Modeling of signal and background. So this is a theoretical uncertainty. So whether we do our calculations at leading order, next to leading order in QCD, next to leading order in electroweak, it depends completely at what perturbative order we calculate our theory modeling. That actually includes or some level of uncertainty encroaches there. So luminosity, uncertainty on precise determination of the rate of collisions, and then when we are doing some theory simulations through Monte Carlo simulations, we can also get some uncertainties from Monte Carlo simulation packages. So the aim is to have the theory precision and the experimental precision kind of match, so that it's not that experimental precision just continues to improve, and we are stuck with our experimental precision at some level. So now I am going to discuss a few examples only. So taking from what Subhodha discussed yesterday. So he discussed the Z Higgs scenario. So I am going to discuss the V8 scenario, and I am going to give you some perspectives of how to do collider physics. So this could be an example from where you can start. So for instance, here I have the beam axis. So two protons collide, and what it produces is a Higgs boson and a gauge boson, or rather a weak boson. So it's a W or a Z boson. So for the Higgs scenario, I consider it decaying to a pair of bottom quarks, which become bottom jets. And because the Higgs is a scalar, for now I'm going to look at the Higgs decay as something called a fat jet. So I'm not very much keen on looking into the angular structure of the decay products of the Higgs. So this would actually improve the analysis further, but let's for now look into the decay of the weak boson. So the weak boson in its rest frame decays to a pair of leptons, L1 and L2. So for a Z boson it would be an L plus and an L minus. For a W boson it would be a charged lepton and a neutrino. So what we do is that, so I showed you three angles. Look at these three angles. These are going to be important. So there's a big angle theta, a small angle small theta, and then there's an angle phi. So these phi and big theta, and this XYZ coordinates, the X, Y and Z coordinates, are in the V8 center of mass frame. So V and H. So it's in the center of mass frame of the V8 system. So and the theta is in the center of mass frame of the V. So the rest frame of the V. So in order to have relate these theta, small theta with the big theta and the phi, we need some Lorentz boosts. So we would need to boost one to the frame of the other in order to do analysis. So how much differential information can one extract from this process? So for 3-body phase space, so we are taking the Higgs as one body and these as two bodies. So it's a 3-body phase space. We have 3 cross 3 minus 4 is equal to 5 kinematic variables, which will completely define the final state. So barring the boost factor, as I discussed, there will be a boost factor. The variables will be the center of mass energy and these three angles. So I'll show you in a bit. Once we write down the amplitude of the PP to VH and the V decaying to a pair of leptons, we square the amplitude, what we end up with are these 9 angular structures. So, you see that these angular structures are functions of this big angle theta, this small angle theta, and there's also phi here. So, these are the 3 angles. So, if we write down the amplitude squared, we get these 9 structures. So, these are the only 9 structures which come about, and a very nice calculation has been done by Hitoshi Murayama and collaborators before, where they show that how many angular structures are going to be present for every dimension operator for every process. So, it's a very interesting paper that you can look for later on. I can actually link it later on when I put the slides up for upload. Sure. Oh, yeah.
So, when we have in amplitude square can be written depending on these 3 variables, capital theta, small theta, and phi.
Yeah.
And in third plate, we have kinematic variables, 5 kinematic variables.
Yes.
So, is it somehow 5 kinematic variables are termed in terms of these 3 variables?
No, these 5 kinematic variables are these 4 and the boost factor. So, these are the 4 kinematic variables, and I have not written the boost factor here. So, those are the 5 kinematic variables that we are talking about. So, yeah, so I'll show you how I squared these amplitudes and how these come about in a bit. So, now I just wanted to compare 2 processes. So, I talked about this VH production, and probably many of you have heard that the Higgs was discovered through the ZZ star channel in 4 lepton final state. So, Higgs was first discovered in 2 channels, the diphoton channel and the 4 lepton channel. So, this is the 4 lepton channel, and here the angles look a bit different. So, one of the 2 Z's is an on shell Z, the other is an off shell Z. So, there are 2 angles theta 1 and theta 2, and there is another angle phi. So, these look a bit different from these thetas here. However, even when we squared the amplitude here, we see that we end up with similar angular structures for the gluon fusion channel as well. So, we get 9 angular structures here and 9 angular structures here, which are not exactly the same. And I will show you something interesting is that, like some of these terms, you will see that they come with squared powers of these trigonometric functions, and some of these terms come with just linear powers of these trigonometric functions. So, when we finally do the phase space integration, the terms which have linear powers in the trigonometric functions, they actually become 0. And so, there should be a way that we do not lose those terms. So, I will discuss those, because you will see shortly that in standard model for such processes like Z Higgs, W Higgs, the longitudinal term actually dominates over the transverse term, because the Z could be longitudinal as well as transverse. So, the longitudinal terms dominates. However, in the effective field theory scenario, we often have some of these couplings only as an interference between the longitudinal and the transverse, which come with these single powers of cosine thetas, sine thetas, and so on. So, if we integrate these out and these vanish, then we completely lose information about these terms. So, there is something called interference resurrection, through which we can actually make these terms non-zero. So, now let us discuss VH production at colliders. So, this is 2 quarks through a W or a Z mediator producing a W or a Z boson with a Higgs. So, you see that here I have given 3 diagrams. So, the black dots basically symbolize that these are vertices which are affected by the effective field theory operators. So, when we, as I wrote before, that when we expand these effective operators, we get these interactions to be dependent on the Wilson coefficients of these operators. So, these operators actually give rise to deformations in various interactions. So, here we see that there are 3 kinds, and the third kind is particularly new because this diagram is not there in the standard model. It is a 4-point interaction, which we will see that it grows with energy. So, here I have already showed you this diagram. So, I also told you that this could be made more differential, and I have told you that for the Z Higgs, once we square the amplitude, which I will be showing shortly, it's possible to probe multiple angular observables at the LHC. So, the LHC can actually see many of these angular distributions, and rather than just studying some cross section or some PT distribution or some azimuthal angle of some leptons, we can actually study these 9 independent angular observables, and we can constrain many EFT directions. So, there are many operators which contribute to such deformations, but for the in the Warsaw basis all the dimension 6 operators are these. So, these are all the operators, and you can look up these operators. Many of these operators have been discussed in previous talks, in Shubhoda's talk and so on. So, there are also CP odd operators. So, we do not only get to constrain the CP even operators, but we also get to constrain the CP odd operators. So, whether there is any presence of CP odd structure in the couplings at all from the present data. So, now what I do is that I write everything in the broken phase. So, I write the Lagrangian, not just, so do not focus on the entire screen, focus on these 4 blocks, and I will be discussing what these 4 blocks are. So, I discussed what these 3 diagrams are. So, when we take all these operators that I discussed here, we open these up, we expand these up, we are able to write down these terms. So, the terms in blue are basically very similar to what the standard model terms look like. So, here you see the Higgs Z mu by 2. So, this is exactly what the standard model term looks like, but it comes with a prefactor. So, this is basically standard model term with a scaling, it is called the kappa framework. So, in the initial days of the LHC studies, more differential terms were not considered, and only these scaling modifiers were considered. So, in some of my initial studies, we only considered these coupling modifiers which only scaled the couplings, but did nothing else. But since then we realized that we could do much better. So, we could actually study some new structures, look at the black blocks for instance, which do not arise in the standard model. So, for example, Higgs Z mu nu, this is a CP even term with a new Lorentz structure, new with respect to standard model, and then we have a Higgs Z mu nu tilde, which is basically a CP odd term with a new Lorentz structure. In standard model there are no such CP odd terms at all. So, both of these terms are missing in standard model. So, these terms actually come from these kinds of interactions, and then we are met with this contact interaction. So, see here it is a very weird looking term, Higgs Z F bar F. So, it is a 4-point interaction which is basically this one. So, 2 F's, a Higgs and a Z or a W. So, these are the 4-point interaction. So, here you see that because it is a 4-point interaction, then there is no propagator suppression here. So, whenever there is a propagator there is going to be a suppression, but there is no propagator here. So, there is no suppression. So, this grows with energy compared to the other terms, and I have listed here 4 couplings. Just look at here, this circled one, delta GZF. So, these are the 4 directions that I will be discussing, which are called the so called high energy primaries. So, I will be discussing that at high energies. So, of these many operators that I discussed, only 4 operators will be surviving, the others will not contribute at all. So, and all of these 4 operators can be encapsulated in this coupling. So, this F actually is like it hides the indices. So, it would be up left, up right, down left or down right. So, there are 4 kinds of couplings here which are hidden in this one coupling. So, this let us forget about this slide. So, here I have written down everything in the broken phase. The reason for writing in the broken phase is that when we are talking to experimentalists, we do not want to impose on them what kind of basis that we are choosing. So, we could be working on the basis that has been discussed a lot of the times in this workshop, the Warsaw basis. There is something called a strongly interacting light Higgs or the Silch basis. There is something called the Higgs basis. There are many different kinds of bases that particle physicists usually work with. So, we do not want to like impose on experimentalists with so many details, because they are already doing a lot of analysis. So, what we can do is we can write things in the broken phase. They can give us constraints on these couplings, and then we can map it on to the favorite operator basis that we want. So, for this case, for example, in the Warsaw basis, this is the map. So, you do not have to go through this. So now talking about the high energy primaries, so there are 4 channels, the Z Higgs, the W Higgs, the WW and the WZ. So even though these 4 processes look completely different from each other, they can be expressed at high energies respectively as the gold stones. So the Z becomes the G0, the W plus minus becomes the G plus minus and so on. So all of these processes can be intertwined. So for example, the Higgs doublet can be written as this G plus H plus I G 0 by 2, and we will see that at high energies these 4 completely different processes, Z Higgs, W Higgs, WW and WZ, actually become correlated. So the same set of operators actually relate all these 4 processes. So these completely different looking processes, just understand this, can be like constrained in the same parameter space, and we will be able to constrain the same parameter space by studying these 4 processes. So they are intrinsically connected by gauge symmetry. So this is, I highly encourage you to read the Goldstone boson equivalence theorem. So it's a very important fundamental thing that comes in quantum field theory. It is possible to compute amplitudes for various components of the Higgs in the unbroken phase. So Shottoda discussed like very similar things yesterday. So I encourage you to go back to it and study his notes. So he discussed about he discussed it in the global scenario. However, when we gauge a scenario, the Goldstone boson equivalence theorem might look slightly different. So whether you are choosing the Arzai gauge, whether you are choosing the Feynman gauge, it might look a bit different. So high energy primary. So I was just talking about these 4 processes, the WZ, the W Higgs, the WW and the Z Higgs. So see that there are these 4 processes and there are different initial productions. So for example, UD, UU, DD and so on. So there are left-handed particles for the up and the down, as well as the right-handed particles, and these are all combinations of these 4 high energy primaries, only these 4. So at high energies, these 4 processes are linked only through these 4 high energy primaries, and you will be able to write these 4 high energy primaries through the couplings that I just discussed a while back, these couplings, these 4 couplings. So it's very interesting, even though you are probably not be able to grasp all the nitty-gritty details of this, but know this, that like using the Goldstone boson equivalence theorem, we are able to relate 4 completely different processes. And yes, VVF is also, it's basically the 5th process which can be tested with this. So I'll show that in one of the later slides. Yeah. Sure. Yes.
And you have these vertices like HZZ vertices.
Yes.
And it is suppressed by inhaled by V, electric wave.
Yes.
And in SMEFT it could be like lambda square, maybe.
Yes. In dimension 6 lambda squared. If you go to higher dimensions, then something else. Yeah.
No, even if one consider, let's say, lambda order of TAV,
yes,
then ZH production in SMEFT will be much smaller than this heft.
So it depends on the size of the coupling as well. We haven't,
let's say for order 1 coupling.
Yeah, so exactly. So it will be smaller, yes.
But it should be same, right? It should have be same.
Because it depends. So as I said, in the heft scenario, we have a non-decoupling regime. So in the SMEFT scenario, we have a completely non-decoupling regime. So the couplings will not be the same. So for the heft scenario and the SMEFT scenario, you cannot choose the same coupling. So when you are choosing a different scale, the couplings you will not be able to choose the same couplings for the case.
That means in heft scenario, this coupling order of very small, like order
yes,
-3, -4.
Exactly,
like.
exactly. So you can map these 2 completely, but in a non-decoupling scenario only. Was there any other question? Okay. So here basically, as I said, through the Goldstone boson equivalence theorem, you are able to relate these 4 processes exactly, and as Tisha mentioned, you can also relate the weak boson fusion channel through the Goldstone boson equivalence theorem, because you have the same vertex there. So you either have the WW Higgs vertex or the ZZ Higgs vertex. So now we can actually map the high energy primaries to the low energy primaries. So I told you that in effective field theories, when you expand out an operator, you get many correlations. So you get some correlations between the Higgs couplings and the triple gauge couplings or the Z pole observables. So, here you can see that the high energy primaries can actually be linked to the low energy primaries, the 4 couplings that I have been talking about. So, these are the 4 couplings that I have been talking about, this delta GZF, and here you see that I have written them as delta GZUL, DL, UR and DR. So, all of these couplings can be written down in terms of these 4-point Z pole interactions as well as the triple gauge couplings. So, this delta GZ1 is basically the interaction between 2 W bosons and a Z boson, and delta kappa is basically the interaction between 2 W bosons and a photon. So, what I am trying to say is that at high energies you can map your observables to low energy primaries as well, because these were measured at LEP. LEP was a much low energy machine than LHC. So, you were able to constrain these couplings at LEP very well. However, these couplings which grow with energy, you will only be able to constrain them at very high energies. So, high energy couplings are linked with the low energy observables as well. So, that is basically what shows that the high energy primaries can be linked with the low energy primaries very, very intimately for these 4 processes, which are linked through the Goldstone boson equivalence theorem. So, as I said that we started with a lot of operators. So, we started with 18 different operators for the weak boson, for the Z Higgs and the W Higgs, but once we go to very high energies, of these 18 operators, 14 of them are no longer important. They do not grow with energy, but these 4 operators do, and we are able to link these 4 operators to the high energy primaries that I have been talking about since the last 3 slides. So, this AQ1, AQ3 and this AUR and this ADR. So, you see that AU, AD, AQ1 and AQ3 can be actually related 1-to-1 with these 4 Warsaw basis operator coefficients. So, now coming to the Z Higgs production, I am going to discuss a bit about helicity amplitudes and how you do the calculations. So, in case you are interested in doing the calculations. So, here you see that for a 2-to-2 process, say a fermion with a helicity sigma and a fermion bar with minus sigma giving rise to Z Higgs, the helicity amplitude can be written down as, so for the transverse part we have this expression, and for the longitudinal part we have this expression. See here that the transverse part is suppressed by an additional factor of 1 by square root of S hat. So, that means that these terms 1 and 1, these are the standard model pieces. So, just when we take the standard model part, the transverse part is way smaller than the longitudinal part, especially in the high energy regimes. However, when we take the effective interactions here, so we write down all these operator coefficients which are hidden in these couplings, which I showed you a little while back, we will encounter scenarios where even the transverse part can become large, because you see that it comes with an S hat. So, this S hat will actually cancel out with this root S hat, or so there will be energy growth even when we take the interference between the longitudinal and the transverse pieces. So, when I take this amplitude, so this amplitude is only for the 2-to-2 process, then what I do is that I include the Z decays. So, then I have all the 3 angles, the big theta, and remember I discussed about the small theta and the phi angle. The small theta was basically in the Z frame, how the Z decays to a pair of leptons, and the phi was basically the angle between those 2 planes. So, then what we do is that when we square the amplitude, we get these 9 terms. As I was talking about, these 9 angular structures we get very clearly from there, and these coefficients sitting here are actually functions of these EFT couplings as well as the energy. So, we can actually write down the squared amplitude, we can decouple the energy piece from the angular pieces, and we can do our study. Yes.
So, like we do, we construct these 9 observables for Higgs style process.
Yes.
Can we do for vector boson fusion by
Yes.
taking jets in as frame and
For the weak boson fusion, it's going to be much more difficult, in the sense that there's like the Higgs is going to decay into something, and there are two jets which are not related to anything else. So you have to take many more angles there. So there will be many more angles at play. It's definitely not be these 9 angular observables. There will be something different completely. So you have to do and check it out. So I am repeating this picture once more because this will come back again and again. So as I said, there's this kappa framework, this scaling, and then this contact interaction, and then there are these new Lorentz structures that we talked about. So EFT validity. So till now I have not talked about EFT validity at all. So till now we have been talking about some Wilson coefficient, say C, and some scale, say lambda. So we have been talking about constraining some C over lambda to the power something. But what if we are doing some EFT with some UV matching? So again I encourage you to look at Joydeep Das talks slides again. So when we try to do some matching, then this EFT validity question becomes even more important. So for example, we can take a very simple case that we can have an SU2L triplet and a singlet vector W prime and a Z prime, which couples to the standard model fermion current. So this is the triplet current, this is the singlet current with a coupling strength of GF, and to the Higgs current like this I H dagger sigma A d mu H for the triplet case, and this is for the singlet case with GH. So when we integrate out the heavy fields, so again integrating out probably has been discussed in the school, or else like just ask me, I will be happy to include those in my slides. So you see here that we are left with effective couplings like this GHZ U or D L and GHZ UR or DR. So in these couplings, some of the couplings are known to us. So for example, G is the standard model coupling, V is the standard model WEV. So we know the G and the V here, we do not know the GH and the lambda. So if we assume some weak coupling, for example if we take GH equals 1 for instance, so in standard model the G is of the order of 0.3. So if we take G of the order of 1, then we have a strong constraint on lambda. So then in our EFT analysis that we do in colliders, we cannot go to like arbitrary high energies in our analysis. So that's what I show here next. So here you see this cutoff line which we calculated event by event, and we found that this is the cutoff for the Z Higgs invariant mass. So you cannot take any events above this cutoff scale when you choose some coupling. So had you chosen a different coupling GH equal to 0.5, this line would have been different. But once you stick to a coupling, then you have to basically throw out events which satisfy this kind of a scenario. So but yeah.
Also, like when you choose lambda, when
Yeah.
the lambda is far away from the electric scale,
Exactly.
then the RG could play very
So RG could actually, so RG could actually, so I don't think I'll have time to go to the RGs, but it's, I don't think I'll have time to go to the RGs, but it's there in the slides. So when we RG evolutions, so you see that many of these operators run down to certain scale, and there are like very intricate dependence on this scale, and there are some logarithms which come about. So this lambda becomes even more interesting when you, this EFT validity becomes even more interesting when you take into account the RGEs. So or a C quark or a light jet. So when we tag a B jet, so some of you may have read about tagging jets. So I may have read about tagging jets. So I'm not going to discuss how you do tagging for jets. So when you tag a B jet, it always comes with a certain probability, like some 60% or 70% of the cases you can say with certainty that this B quark has become a B jet. So but for other cases you cannot, so you lose a lot of events. But it's also possible that it didn't originate as a B quark, it came as a light quark, but it faked as a B jet. So that's also possible. So the more the fake probability, the bigger the background is going to be. You have a question? So it's important that the experimentalists study and reduce the fake background. Important that the experimentalists study and reduce the fake backgrounds to the maximum level possible. So they do that. So we include all of these backgrounds, and we do a collider analysis. So this So this is something called a cut flow table. So basically we in a collider analysis we require certain steps. So basically we require that there is going to be one very fat jet with a radius of 1.2, where there are going to be 2 B meson tracks inside. Then we require that there are going to be 2 opposite sign same flavor leptons, because we are having a Z boson here. So, the Z boson decays to an electron and a positron, or a muon and an antimuon. So, we have 2 opposite sign and same flavored leptons, charged leptons. Then we require that the Z boson, actually the 2 leptons, we reconstruct them and they peak at the Z boson mass. So, that is why we require that the invariant mass of the 2 leptons peak around the Z boson, and so on. So, we require all of these cuts, and we see that for the signal we get certain efficiency. So, with every single cut that we put, a certain number of events they are thrown out, that they are not included even for the signal. But we must ensure that whatever cut we are choosing, the signal's efficiency is much more than the background's efficiency, because our aim is to reduce and remove the backgrounds as much as possible. So, this is basically the framework how a collider analysis is done. I do not know like how many of which generates the hard process. So, it is either the 2 to 2 process that I talked about, the PP going to Z Higgs. It includes the resonance decay. So, the Z boson is decaying to a pair of leptons, and then we also do something called the PDF sampling. Then we have the next step called the parton showering. So, the initial quarks which are in the picture, or the gluons, they can shower. So, the quarks can actually shower into photons and gluons, the gluons can shower into gluons, and the final state particles can also shower, which are called the final state radiation, or FSR. Then we have a step called hadronization, where we form the baryons, the mesons. Then we have a step called underlying events. Then we do the detector simulation as I discussed here, and then finally we do the event reconstruction. So, we identify the particles, whether the particles are leptons or photons or jets or some missing energy or so on, and then we do something called a jet clustering and so on. So, have a look at this if you have any questions. So, it is very short time to discuss this, but I will be very happy to take your questions later on. So, this graph did not come at all. So there is a gray blob here. So, what I was going to say is that because of the Goldstone boson equivalence theorem, I told you that these 4 processes, W Higgs, Z Higgs, WW and WZ, they are all connected along with VBF. So, you see that we can map these 4 processes into the plane of the triple gauge couplings. So, I told you about the high energy primaries and the low energy primaries. So, remember here we discussed the high energy and the low energy primaries. So, these processes, the WH, the Z Higgs, they can be mapped on to the low energy primary parameter space as well. So, here you see that the same processes, actually Z Higgs, WZ, they all fall in the same parameter space. So, LEP had already constrained this process, these processes, and the region was supposed to be this big, and now through LHC we are able to constrain this very narrow region. So, LHC actually improves the precision by orders of magnitude. So, without cuts we had the signal over background to be around 5 over 160, and then we did something like called a cut based analysis, a regular cut based analysis, and we found that the signal over background became a quarter. So, from 5 over 160 to a quarter, and then we used a machine learning algorithm, a boosted decision tree, a primitive machine learning algorithm, and we improved the signal efficiency or the signal over background from a quarter to a half. So, that is the power of including machine learning tools in collider analysis. And you see here that many of these couplings were constrained, and then one was able to constrain them even better at the LHC, and if the FCC is ever built, these constraints would become sub per mil. So, we want, as I was saying, we need a lot of precision. So, sub per mil precision would be available, we will be able to achieve those at future colliders, but even per mil precision is going to happen at the end of the run of the LHC. So, I discussed the contact interaction here. So, here basically I included the 4-point interaction, this one, but I did not talk about these angular observables yet. So, in the same vein we can do the analysis for the angular observables, and we can see that we are able to constrain the angular couplings, this kappa ZZ tilde and the kappa ZZ, to the order of a percent or even stronger. So, we are able to constrain the CP odd couplings as well as the CP even couplings. I am not sure how well this is visible from the back, but know that collider analysis are able to constrain these couplings to percent level or better. So, we need even more precision in the future, and we see here that the experimental collaborations usually take a single operator at a time and do their analysis and give some bounds, but it is important to take all the relevant operators at a time and do the bounds and present the results, and we see that once we do that, one can achieve even better bounds than what the experimental collaborations give us. So, Shubhoda, how much time do I have left?
3 more minutes.
Okay. So, I'll not go into the WW channel for instance. So, I'll just like close with the theory uncertainties in EFT analysis, which are very important. So, for example, I think Joydipda and others have covered bits of it. So, theory uncertainties in EFT analysis. So there could be ambiguities in operator coefficients. So, for example, when we take a dimension 6 operator, do we keep only the linear term? Do we keep till the squared term, or do we take dimension 8 operators? So, that is an ambiguity that leads to some uncertainties. Similarly, validity of perturbative expansion is another source of uncertainty. This is what Joydipda was saying, the RG evolution effects alter the behavior of the theory. So, this describes how EFT couplings vary with energy scales. So, EFT couplings, when we say that we have constrained the EFT couplings, the answers are at a fixed scale. When we want to know the results at a different scale, we need to use the RGEs. So, these are in the later slides, so you will be able to see these, and there can be inconsistencies while matching to a model. So, whether the SMEFT is a good approximation or the HEFT is a good approximation, this all depends on the kind of model that we are trying to match with. Also, at what order we are stopping, are we stopping at dimension 6, we are stopping at dimension 8, and so on. So, I am not going to go through these slides, but there are some interesting slides. You will see that how next to leading order effects, I did not actually intend to cover these, but how next to leading order effects can become very, very interesting and important. So, I am just going to flash a result for WW. So, whether we take a QCD correction to our backgrounds and whether we take a QCD plus electroweak corrections to our background, the bounds can actually change significantly. The reason is that, the reason is very, very simple. For WW process, you see that even in the standard model, the cross section decreases significantly with very high energies. So, that is because there comes about some negative Sudakov factors which makes these cross sections very large. Usually, the collaborations do not include such electroweak corrections, or even theorists do not include such electroweak corrections. But for gauge boson, dye boson production, or any electroweak processes that we study at LHC at high energies, it is invaluable. If we do not consider the electroweak corrections in our studies, we get bounds which do not make much sense. So, that is what I am showing here, that we can see clearly that by taking or not taking the electroweak corrections to the backgrounds, we get completely different bounds. So, I stop here, and I would encourage you to join the LHC EFT working group. So, this is a clickable link, so you can all join, and we have monthly meetings there. So, if you have any interesting idea pertaining to EFTs, you can let me know or let the other conveners know, and we will be happy to include you in some of the discussions. So, we have topical discussions every single month. So, thanks a lot once again. Yeah.
So, sometimes people write most general structure of couplings instead of writing EFT operators and then obtaining.
Yeah.
Although those structures can be obtained from EFT.
Right.
And CMS Atlas
Yeah.
papers also published.
Yeah.
Means their studies also based on those most general structures.
Right.
Is it because those means that approach is more relatable with experiments, or maybe one of them is more applicable to classify models?
Yeah. So this approach used to be like in the vogue with CMS and Atlas before we formed the EFT working group. So because experimentalists did not think about this, so they wrote all possible modifications. But the thing is that all these modifications do not, when we do it from an EFT perspective, all these modifications do not happen at the same order. So from dimension 6 you get some structures, from dimension 8 you get some structures. What they used to do is that like they wrote all structures which would come from an addition of all dimension operators. So that is no longer encouraged by the EFT working group, and experimentalists are slowly phasing it out.
One more thing. So in addition to why we want to study higher dimensional operators, we are not limited to just Kappa framework, because of we want to go more on deeper understanding of new physics, right? But if we are limited to Kappa framework, then in NLO corrections, Kappa framework doesn't allow UV cancellation.
It won't, because it's not gauge invariant.
Okay, right.
So unless you write all the operators, the study is completely not gauge invariant.
That's
so
why we need.
yeah, you need to include all operators, especially for loop calculations.
More questions?
I think people are tired.
Okay, so if not, let's thank Shankho for a wonderful talk. And I have the privilege to do the honor to felicitate him with a traditional gamosa and a piece of memento. We have a very important announcement, because today we have a dinner, and that will be at 7:30 in the B-type community hall. So I think Ovik has sent a link, I mean the Google Map address, how to go. Then we expect to see you all there. There is another point which I would like to mention, is that there are two things that that you need to do. One is a feedback form which we will circulate tomorrow. So it is a customary that you actually fill that up. Do not give very bad comments about us. And the second is actually that we promise that those who have registered as a PhD scholar or below, we are going to return your registration fee. So there will be another Google form that we will be sharing with you, and we urge you to fill that up also and submit that by tomorrow. So these are the two couple of requests, and we will see you all in the dinner. Okay. Dinner time is 7:30. 7:30. So yeah, we can go along a little. I mean, it doesn't start at 7:30 and finishes in 7:35, but we are likely to. Okay. Okay. So see you then.